now I think we can start. Good morning, ladies and gentlemen. Thank you for creating time to come and learn. I'm seeing questions. Yes, you are going to get certificates, electronic certificates, not hard copies. We are going to send to all of you. The ones who have participated, you will get your certificates. So worry not, we have your information. When you were registering, we captured your email, so we should be able to send you the certificates. So at this moment, I want to hand over to our facilitators, and we continue from there. Thank you very much. Dr. Helen, the floor is yours.
Thank you so much, Dr. Runyararu. A very good morning to everyone. Welcome to our day 6, and it's a day that we're planning to have a wrap-up of most of the things that we've covered. Without wasting time, I'm going to share my R such that I just go through what I'm supposed to cover last, the last bit that we had yesterday, and then I'll hand over to Professor Susan to proceed with her last part as well. So I'm going to share my R screen. It's just a recap because we had some participants who are saying that they didn't get clearly the last bit that that I was covering because of the time issue. So now, remember what we are supposed to do. We are still using our data set. I kindly encourage you that you load the required packages, and after loading the required packages for today, you also import your data in R. We are still using the lab2 underscore data, which in R I named as object. In case you want to clear something within the plot window, all you need to do is to type graph off, and then everything will disappear. I want to do that such that I've got a clean window, and then we'll start from there. Graphics off, and then I'll run that. The moment I run, my plot window clears and becomes, and there's nothing there. So let's start now. I'm going to learn my packages. Remember, when all the packages are installed, all you need to do as you start maybe your new day, you've come back to get back to your work after a week and so on, all you need to do is to load your libraries. I'm not installing again because I already have the packages on my computer. So I load my packages. I hope you're doing the same. And then the next thing that I'm going to do is from my working directorate, because I mean, the data is still there. I don't need to redo it again. I already know my working directorate. All I need to do is to run it. That's the reason as to why I encourage you that you always put all your commands in the R script, because the moment you put them there, you can even reuse them every now and then, such that you don't have to rewrite the commands. Provided you know what each command means, then it will become very simple for you. So given that I'm still using the same directorate, so I don't need to go through the procedures that we used on Monday. All I need to do is to click on the line, and then I import my data set, okay, which I named object into R. For me to show that it's successful, of course, I won't get errors, and all will be well. So I'm going to ask in the chat, if you've done it first, you load your data and then in R, and we proceed from where I stopped yesterday. Have you loaded your data in R now, such that we proceed? Just do a quick of go library, load the libraries we need, then import it. Just use the same working directory, because I understand you've got you have a folder on your desktop, so it should be very easy. You don't need to do anything again, and then we can continue. From the chat, I'm seeing that a great response, that people now can quickly load the packages as well as importing the data in R. which is a very great step when you're learning this package. So now let's proceed. Yesterday, we looked at linear regression, the little part of the theory, and then we see how do we do it in R. Now, we say that within R, I'm just doing a quick recap, and then we'll go on to the part that needs more explanation. I say that we use a command LM, okay, linear model. LM is linear model. So within R, we use the LM command. In case you need to get more information about LM command, all you need to do is to use help within R, and then it will give you more information on how you can get the LM command. So I used an object model, like let my model be equivalent to the whole of this particular expression because it's very big and I don't want to carry it on. So R gives me an opportunity to label it as a model such that I can use any other word and then things become very easy. So I use price. Price is my dependent variable. Remember, in this case, I'm only using weight. One independent variable. This implies that I'm considering a linear regression, a simple linear regression model. So price as a function of weight, and then I pick everything in the data diamond, which I got earlier, and then I run that. Okay. Oh, sorry. Somebody was telling me someone complained about the screen. I guess now I think now it's clearer now. Are the words clear now, or I zoom more? Okay, fine. Okay, yes. I was zooming, so I guess now the words are more clear. So I considered model, and then my LM, the model, then price, a function of weight. I called that as my model, and I went ahead to find the summary. When I run summary, it gives me an output of what we went in yesterday, but I'm not going to do a lot of details on this. So within my particular output, what it gives me a summary of the residues. It gives me the coefficients, that is the slope, the regression coefficients. Most of the time, we are used to the line of equation, y is equal to bx plus c, which has got an intercept and then also our slope. So transferring that particular knowledge, the estimates are my slopes. So like we said earlier, as you move on, you have to ensure that as you interpret your findings, you have to match them with what exactly that you are doing. Remember, I'm looking at the price of diamond, attributing it with different variables. But because I'm using a simple one, I considered only weight. And with a minus 211.2, in this particular case, in case I'm considering the intercept, in case I write out my model, you find that I'll consider the intercept when weight is equal to 0. But when you look at it in reality, when the price is negative, it really doesn't make much sense. So in that particular case, we can do away with the intercept. Now, we looked at another important parameter, our slope, the beta naught, which is 7456.8 on the weight. And we said that the explanation that we attached to this, that a unit increase in weight causes the price to increase by this particular value of 7456.8. So you have to check, because it is positive, then we'll tell, in this particular case, it tells us the direction that will be in the positive direction. And for us to have a conclusion on whether there is a relationship between price and weight, most of the time, we look at our p-value, the probability value, and the level of significance that we consider when it's less than 0.05. And vividly, when you look at our result, which is which is less than 2e minus 16, that is 2 times 10 to the power minus 16. It's far, far, far very small, implying that there's a statistically linear relationship between weight and price. And we explained about the multiple R squared, or the R squared, which is the coefficient of determination. And this particular case, it is 85%, which means that the model that is being created is able to explain 85% of the data that we have on the dependent variable, which is price. And remember from yesterday's explanation, we said that in case of a simple linear regression, R squared is enough. But as you keep adding in different variables, then it implies that it's always important you consider the adjusted R squared, because each time you add a variable for it, it keeps adjusting. Yet for the R squared, what it does for it keeps increasing. But most of the time, in case of a simple regression, the R squared and the adjusted R squared are nearly the same. Okay, we had our F statistics and then the overall P. That is what we had. So now I'm going to move on. That was just a recap on how you can explain your various outputs, because at the end of the day, as you fit the model, you want to find out, is there any relationship between the independent variables and the dependent variable? Now, it is also quite important that as we move on, we need to test the different assumptions of a linear regression model. Yes, we looked at them yesterday, and Professor Susan as well went ahead to give us more details to explain them very clearly. But now we need also to check the residues. Yesterday, I said that the residues, this is the difference between the observed value of the dependent variable minus the fitted values. The fitted values, it is the line of the best fit, or you can call it the line of best fit, the fitted values, or the predicted line that we put together to see if we can be able to predict the outcome. So now I move on the part of the residues. We want to see, because by the end of, we want to test when it comes to residues, what we want to find out, does the residues have constant variance? Because remember, with the method of the list of squares, which I mentioned about yesterday, we want to minimize the errors such that they are as small as possible. So we use the least square methods. And so in this case, now let's check the residues and check. Remember how I define a residue? That is the difference between when you look at a fitted line and then the observed value, that length in between is what we refer to as a residue. And we want to minimize the sum of errors such that it is really, really very small. So for us to get the residues of a particular model, all we need to do is we use a resid command in R. So what I decided, I created an object called model.res. And I said, let's this one, model.res, be less or equal, that's an assignment to my command. And then inside here, I want to get the residues of my fitted model, which I called model. That's why when I used model here as I assigned my linear regression, and it's the same reason as to why I'm putting the name here, because I want to get the residues of my model, of the model that have fitted my data. So I run this, and the moment I run it, because I've assigned an object, it has not given me the outcome. In case you want to see the outcome, then you type the object on a separate line, which is model.res, and then you run it. Of course, as you run it, it will give you 100 observations, because remember, we've got 100 observations. And so those are the res that we have. All right. So now let's try to fit and see. We want to plot our independent variable, which is the weight, against the residues or our fitted model, and we see. So now I consider the plot command, which I believe that now most of us have seen it often. My X variable, which is diamond, I pick the weight, and then my Y now is going to be the residues that I'm going to consider. I can label the Y, that my Y lab is equal to put label residues. My X label, put weight. Hope you're seeing my command, and then it has got a close here. So all I do, I run it. The moment I run, it gives me the plot. When you look at in now my plot section, there is a figure there. So I'm going to zoom it out and then we see what happens. But in case you run this second line, the AB line 0, 0, I'm telling R that give me a horizontal line. It's the one that gives me the horizontal line at 0 when throughout the plot. I'm going to run it, and then I'm going to zoom out that particular plot so that we do it very well. In case you want to clearly see your plot, I mentioned you click zoom. Okay, you click zoom and you will be able to see your plot very well. So I'm going to stop sharing, then I show you my plot. Okay, now I'm going to show you my plot for the residues. There we go. Okay, but what we are seeing, it's quite interesting that we say that one of the assumptions is that the residues are supposed to have constant variance. We want to check if where it's constant variance. But when you look at this here, you'll find that the moment we fit, as you check the residues, they are increasing in proportion with what? With weight. So you can look at how my dots are, because we are trying to check, and you're trying to see that they are increasing as weight increases. So it's implying that it is violating the assumption for a simple linear regression model. What we are going to do for us to reduce noise or to reduce the variance, we are going to do a transformation in our data such that we reduce the variation within our data, and we are going such that the assumptions are not violated. So I'm going to go back to R, and then I rerun my model again after transforming the two variables, the price and then the weight, by using a natural logarithm. How do I do it in R? Let's go there. Okay, there we go. Now, what I'm going to do, because the assumption is being violated, the residues are increasing in proportion with weight, yet they have to be constant from the plot that we have just seen. Now, I'm going to go back in my data set. Remember we talked about data manipulation. I'm going to create a new variable within my data set, and then I tell R that on this new variable, which I'm calling log weight, okay? I'm putting this diamond, and then within the diamond data set, I'm creating a new variable, which is called log weight. Let it be equal to log, okay? Are you seeing? Log, the natural log in R, we use the log command. And then I'm asking R that give me the natural log of weight in the diamond data set. I do the same for price. I create another call within my data set, which I call log price. And then I tell R that log price will be equal to the natural logarithm of price. What I do, I run my commands, okay? I do the same with price because the variance was big. For me to check if what I've done is right, remember what we said? Let's run ahead and check the first 6 rows, whether it makes sense. So in case I do that, I run again. This is what happens. When I run, I see that already my data is there, but this time around, I've gotten another column, which is log weight, the one that has been transformed. I've got another column of log price, which has been transformed. But keep in mind that still in my data, I've maintained my price and I've also maintained my weight. Okay. I'm going to ask in the chat, are we on the same page? I'm just revisiting what we had yesterday. Are we on the same page? Okay, fine. Okay, I'm going to slow down and then I'll proceed. So let me ask in the chat again, Have you understood how to do a transformation on a variable by using log? Type yes if it's okay. Okay. Okay, let's proceed now. Now, having created, used transformation of my weight, now I'm not going to use the weight that I had before because it was giving me a big variance. See, this time around, I'm going to consider the log weight and then the log price, and then see what is going to happen to my model this time around. So what I do, I changed the object name. Initially, I used model, but this time around, I considered model OG, model log as my object. We talked about object, and it could be, you can name it anything. And I said, I brought back my LM command. Okay, now this time around, instead of using the price that I had earlier in my data set, I'm telling R that use the log price, the transformed one, which is this one, log price as a function, log price as a function of log weight. And I'm telling R, I'm still using my diamond data set, data equal to diamond. What I do, I click and I run my line. Then I can get a summary. When I run a summary, I get similar results. Check the results that we are getting the moment you run summary. So still again, remember what you're seeing here, up here, this is our model. It calls it our model. And then it also gives you the residues, the summary of the residues that we are considering. And we move again to the coefficients. It is the same thing, but what we are saying here this time around, that the values that we are getting have been scaled. They are no longer big like before because we are using the price and the way that has been transformed. But still we are saying that there is a significant relationship between price and weight when we use a what? When we use a log weight and a log price. So now let's see what happened to the residues. Are they still increasing? Are the residues still increasing in proportion to the weight? Or this time around we can see that they are constant. Okay. Somebody is saying that I paste the log code. I'll do that. There's noise in the background. There's somebody who is, maybe we close the door. Okay, I've pasted the transformation codes in the chat. Now, somebody's still asking the chat that how do we explain the second model? We use it's a similar explanation, only that this time around, we are using a transformed model, but the explanation is still the same. Now I'm going to move on to to plotting. Now my residues, okay? What's going to happen? What I'm going to do, like I told you earlier, you can manipulate your data points. I'm going to first do something, and then later, I show you a different command on how you can bring out all the commands together. No, we can leave it. We have no choice. To stop, maybe. It's affecting the participants. Sorry, we are going to work on the noise that you're hearing such that I will tell the person to stop. Okay. Now, before I use this command, let me first run what we had earlier. We had this particular command previous in the one where we had not transformed. But what I'm going to do here, remember what I did? I used the what? A log price. I used a log, the log weight. So what I'm going to do, I'm going to come here and change this. Instead of now weight, I'm using log weight, okay? And even the model that I'm using, it's no longer, even the model that I'm using, it's no longer the model res. This time I'm using model log, okay? If I take you back, just here, we got the residues for, we got the residues for the model that we created. So I can do the same. What I can, I'm going to do the same. I'm just repeating what I had previously. What I'm going to do, I'm going to create the rest for the created model. I'm just going to get this and then copy it down there, but I need to change the settings. So when I come down here, I know I already have my, so to get the list of residues, this time for the after transformation, okay? After transformation, I'll send you an updated version, but it's all the same. I can call this one, I can call it model res 2, okay? Such that is different from the first one. And this time around, the res for the log, for the model log. And this one, I'm renaming it to 2. I also run it, okay? And then I can as well check how they look like for the case of the transform. Still, they are 100. And now I run a plot, that plot for the case to check whether I've got constant variance. Okay. Now I want to run the plot and see this time around. How does it look like? Remember now, it is diamond, then I'm picking the log weight, not the initial weight we had. And then now the model that has the residues that have been transformed are the ones that I'm plotting. So I run the command, and then also in case I want to check the horizontal line on the 0, I run that command. And then yes, in the chat. Okay. That I reduced the speed. All right. Let me copy the commands and in the chat, and then you run yourselves. I'm pasting in the chat. Okay, I'll put the commands in the chat. I've also put in the Q&A. Hope you've been able to get them. I've also put in the chat, please check. Okay, now what I'm going to do, I want to share I want to stop sharing, and then now I show you a new plot. In case we do the transformation, what happens? Yes, this is now what we are getting. I've zoomed my plot out. What we are seeing that this time around, we are seeing a constant variance. And in this particular case, we do not see any pattern. Yet initially, we are seeing a pattern whereby the residues were increasing with weight. But the moment you do the transformation, in this particular case, what we are seeing is that the upper part is almost equal to the lower part. So this is the plot that shows that the residues they've got constant variance. However, there is also another one that we need to understand, whereby we need to check for normality. Now I'm going to use another command that brings all these things together, that checks the residues at the same time shows you the normality. I'm going to stop sharing this and then go back to my R command, my R studio. Can I ask, I'm asking in the chat, are we together? They're still complaining about the background noise. Okay. Okay, we are sorry about that, but we are going to rectify that. Okay, so now let's move on. I'm getting comments that you are following. We still encourage you to use our YouTube in case there's something that is not clear, as well as such that you go on your own pace as you listen and then you pause, and things will get more clear. Okay, so now I'm still moving on to, I'm still using my model log, the one that is transformed. So kindly, I want to have the different plots on one panel or like on one page. It's what I want to do. So what happens, I use a command, PAR, then in bracket, MF row, which is equal to C22. So in this particular, this command means that split the plotting panel into a 2x2. This is what it means. A panel, it's like a page, and then split my plottings in a 2x2. In case you put a 1x1, then that will be the normal font that we are getting. If you split a 2x2, you're telling that I'm going to have 2 figures in the first row and then 2 figures in the second row. So let's try that out. The moment I run that, it doesn't give me any output because I haven't yet plotted anything. So what I'm going to do, I use now the command plot. I tell R, I'm using the command plot, and in it, I plot my mod log, okay? When I run that, are you seeing what is happening? R is telling me that the figure margins are too large. They are too large because I made the wordings within the different workspace to be large. So what I'm going to do, I'm going to reduce a little bit such that I get a figure and then I show it to you. So to do that, you do Control minus on my computer. To other people, I'm not so sure. So in case you're also getting, but in case it is the normal font that you're working in and you've not zoomed anything, automatically you will get the plot. But if you want to zoom out, type Control minus, and it's what I've done. So what I'm going to do, I'm going to rerun again and see what happens this time around. Okay, I click on it and then I run. Now, the moment I run, hope you're seeing now what is happening to my plot. I've gotten 4 plots because I first told R, I first plotted a panel which is over 2x2 grid. And now I told R that plot mod log, and then we see what is going to happen. In case I zoom this out, okay, I'm going to stop sharing my R studio, and then I zoom out, I show you the plot that we've gotten. Okay, there we go. So now this time around, we are able to see different 4 plots, but let's just go through them quickly and see. The first plot is what I was showing you when I plotted it independently. You know, you can have plots on a panel or on a page when you've got more than 5 figures or 4 figures, or you can even just plot one by one. But sometimes we do this to make our work more appealing, and we reduce on the number of pages that we are using. When you look in your left-hand side, the upper figure, where I'm putting my cursor, it is the plot that I first plotted, which was only one that was coming out. But now, as we are seeing here, we are seeing that the residues against the fitted values, we are seeing a constant variance. We don't see any pattern there. But the good thing with this particular command, it also gives us the plot for normality. And what we are seeing in this particular case, it is very interesting that most of the data, it shows you that the regression line, that most of the data is on the regression line, which proves normality. The other one on my left, the bottom one, for it, for those of you who have heard about standard normal. In this particular case with a standard normal, the mean is 0 and the variance is equal to 1. It is also showing us that still, this time around, the variance is constant. So you can use this particular command to check mainly the two assumptions that there is constant variance in the residues, and also they are normally distributed, which it gives you the first plot, the above 2 plots, and you can now proceed. The moment the assumptions you've proved the assumptions correct, then you move on with your data. I'm going to ask in the chat whether the picture is okay. Is it okay? And I proceed? Great. Okay, I'm going to stop sharing this since now the figure is well explained. I'm going to go back to my R Studio and continue. Okay, I'm going to zoom again such that we all see very well. Okay, my figures disappeared, like figure margins are too large. The moment you zoom out, your figure will disappear. But like we mentioned earlier, if you want to get well versed with a package, don't worry about the rates that you get, because each rate that you get, it muscles your mind to find out what could be the problem. And the moment you solve it, you're good to go. All right, that is the part that I've finished sharing. I'll share an updated version of the script, such that you'll also take a quick look at it again. Within the same script, there are also other commands that I'm not going to go through, but they're also interesting in case you want to see what happens to them. But we've already looked at the scatter plot. You can also plot when you're having the regression line. For them, they're just like, in case you don't do this, you can use this plot. They're all the same. That's why I'm not rerunning them again. So now what I'm going to do, you can also ask the confidence interval in case you're interested, the confidence interval regression line, by using the conf it of your model, of the regression model that you've set up, and then it will give you the regression models. So now while you're moving down, lastly, I want to share with you about the multiple regression model. We've just looked at the simple regression model, and we said with a simple regression model, we could only consider one independent variable. And also we looked at the characteristics of a good regression, of a good model. We said it should be as simple as possible. It should have at least few variables, and at the same time, it should explain about 75% of the variation in the data. We looked at that yesterday. And when it comes to multiple linear regression, instead of having one dependent variable, this time around, you can add as more variables as you can, provided depending on the data that you have. And it's also important, as you're going to go into the multiple linear regression, still to check the different assumptions of linearity if they are not violated. And at the same time, you need to check whether the independent variables that you want to check on your dependent variable are not correlated, in addition to the other assumptions that we mentioned earlier. Okay, and most of the time what we do is that you plot a scatter plot to check if all is well with your data. So what I'm going to do, within my data set, I want to do a multiple regression using weight. Weight is already there, but I want to add length, I want to add width, I want to add depth. However, you can add as many variables as you can, depending on your data. But at least you have to make sure that each variable that you add, it doesn't violate the assumptions. So what I'm going to do, I want to see a scatter plot of how they look like. How does weight, length, and then width and the depth look on my scatter plot? Because most of the time that's how the visualization quickly you can look at how it looks like. So what I'm going to do, I'm going to plot my grid again by running Perl mfcall, okay, which is equal to a 2x2. I'm telling R, set for me a grid panel over 2x2 matrix, okay? That is 2 rows and 2 columns. I can set that. Kindly watch what is going to happen, okay? Then I will run my diamond. Look what it is still telling me, that there is an error in the plot.new, figure margins too large. I need to reduce my font again such that the figure that I get is able to fit in the plot window. That's the reason as to why you're seeing this particular reds. And the moment I reduce the font, then I will not get those reds anymore. Since you're using the same font on your computer, I believe you're not getting these reds that I'm getting. But it's also a way on how you can still learn R. I'm going to reduce such that we do we follow together. Okay. I'm plotting control minus such that it takes me back to the font that I need. So what I'm going to do, I'm going to restart again. That I need, you see, the reds have disappeared. I don't get them anymore because initially they were complaining. So you don't need to get scared. Then I want to plot price as a function of weight. That is the grid. Kindly look in my plot window and see what is happening. Okay, so far I've gotten one plot. And then I want to see price and length. What is it going to do? Because in the Perl, I commanded it in the Perl command that it is MF call. So that's why you're seeing now I'm getting my second plot downwards below the first one. When I run the second one, it is going to go to the left to create another plot. And then when I run the last one, and that's what it appears like. So what I'm going to do, I'm going to zoom it out and then I'll show it to you. Okay, for now, let me stop my R command and then I share the plot that we have. Okay, this is what we are getting. Yes, when you look at this particular data, as we are learning and you can put all these things in now, you can replicate all what we are doing on your personal data. We've already seen the relationship between price and weight. Yes, we can see a linear relationship. And then you can see price and width, though we still see that they curve like, but a little. But the moment we do transformation on all the variables, we know what we expect now. And the same thing we are still using within price and length. There is a relationship, like price increases with the length, and then the same also applies with the what? With the depth. So I'm going to go back to R, since because before we run the multiple one, it's always good, you see, whether the dependent variables that you are plotting, there is a linear relationship with the dependent variable, in our case, which is price. Okay, I'm going to share again my R Studio, and then we'll move on the same page. Now, in order for you to do away with the plots that you are having, the grid of a 2x2 plot, such that you go back to the normal grid of R, what you do to go back to the normal font, you run, let me zoom out again. Okay, I hope now they are clearly seen. Okay, we've just run that part. Now to get back to the original graphic device, all I need to do, I run the same command, okay? But this time around, when I come to the C1, instead of a 2 by 2, I tell R that you put 1 by 1. It's a matrix of 1 by 1. So there's no segments that you've put. So I'll run that such that in case I run my plots again, then it implies that it will give me the normal plots when they are not joined. Don't worry about the rates that you are seeing. I've already explained why they are there. I've zoomed out and I'm not working in the normal font. All right. Okay. Now I want to run my multiple linear regression. This time around, I call my model 2. Okay. The one of simple, it was model 1. But this time around, for multiple linear regression, I create an object which is model 2. The command is the same. It is LM. And then we've got a price this time as a function of weight. I add length, I add width, I add depth. As we further on, maybe in the follow-up, you can as well even do some interaction within these variables to give you interesting analysis. And it's interesting at the same time detailed to give you concrete information of what you want to convey to the audience. So what I'm going to do, also I'm telling you that I'm considering data diamond. So I run this command. Okay, when I run it, I need to get a summary of what it is telling me. I go to the summary model, the summary of my multiple linear model that I ran the previous line. Okay, so now let's check the results that we are getting. Interesting. What we are having still, the output is also similar to the one of simple linear regression. However, this time around, we are having more variables within our model instead of the one variable that we have. Still in the output, the printout, it gives us our model, the multiple linear regression model. It gives us the residues, and it also goes further to give us the estimates for each, or the slope for each. Because when you look at this, when you look at our estimate, we are having, our weight is 947. You look at the length, you look at the width. These are the slopes for each variable that we are having. We've got the standard error, we've got the t, and then the probability, the p-values. So now, what we are supposed to have it as you're interpreting your multiple linear regression, and we say that you can explain the coefficients like we explained earlier. It is the same thing. That a small unit a unit increase in the independent variable causes your dependent variable to increase per the value of your slope. Okay, that one we mentioned earlier. But since for the case of multiple linear regression, implying that now you've considered all the variables, you have to come up with a conclusion. Because what we have done, we did the univariate analysis, we did the bivariate analysis by running two variables. Now for the multiple linear regression or the simple linear regression, we'll move further to consider all the variables that we are having. And the multiple linear regression or the regression linear models, they were suitable for this kind of data because our dependent variable was continuous. But look at the back of your mind, we are considering diamond. In reality, when you look at how diamond looks like, and within this particular data set, what they are saying that they considered there is length, there is width, there is depth. But in reality, in case somebody wants to buy diamond, okay, what could be the most important thing somebody would consider? Because when you look at our result, it is showing that among all the factors that we considered in our model, it's only weight that it is significant. Okay, which is 1.3 times 10 to the power minus 7. Sometimes if you want to check if a variable is significant, you can also check on, besides, usually there are stars. Here I've got 3 stars and then auto stars or 1 star. that one also can support you to tell that the variable is significant. So looking at the output that we are having, we are seeing that there is a statistical relationship between weight and price, because our p-value is significant. Yet there is no statistical relationship between length, width, depth on price, because the p-values are not significant. For the length, we are saying we are having 0.13. For the width, we are having 0.149. And then for the depth, we are having 0.5998. So when you see such results, sometimes when you're doing your analysis, you do not need to pull yourself away from what is happening in reality, or away from what you know, because most of the time, let's look at it in our example. Yes, in case you're going to, when you're looking at diamond, let's look at, you're going to buy diamond. Most of the time, do you mind, I mean, is really the length important? Is the width important? Is its depth important? Or the weight in actual sense? It's a one that most of the time that it influences the price. Then now you can attack that explanation that yes, okay, basing on the model that I have, of all the variables that I considered, it is weight that practically determines the price of diamond. I'm going to go to the chart and ask, is that clear or not yet? Okay. Are we allowed to report transformed data? Yes. Okay, yeah, you report, but you have to unlog. Thank you. Okay, they're saying that it's clear. All right. Yes, there's also another question that popped up about the stars. Okay, okay. Okay, within the multiple regression, kindly note that price is a function of all our other variables, weight, length, width, depth, that we are considering. It is not weight which is the function of price, not the other way around. It is the dependent variable which is the one that is being influenced by our dependent variables. Okay, now to talk about the stars, I was saying that sometimes, in case you cannot tell, sometimes people find it hard to tell which variable or which p-value is significant. But when you look at your p-value column, where you're seeing my cashier, you look at the adjacent of a particular value. For example, in this particular case, we are having 3 stars, okay? And then at one point when you're doing your analysis, you might see like 2 stars or 1 star. And even they're actually explained down here, the significance codes. The 3 stars, most of the time, it is 99%. Then the 2 stars, it's 99, then 90, and then 95. But the point is, where you see the 3 stars and then the 2 stars or a 1 star, that is enough indicator to tell you that yes, this variable that I've considered in my model is significant. And so there is a statistical linear relationship between my dependent variable and my independent variable. So when we move further, we say that in this particular case, the moment you consider a multiple linear regression, it is always good to consider an adjusted R-squared to check the amount of data that has been explained by the model, the amount of the data that has been explained by price. And in this particular case, when we check the adjusted, because as you keep adding more variables in your model, what R does, the R adjusted for it, it adjusts all to the variables, yet for the R squared only, it just keeps increasing. So you need to report that. And we are having 85% of the data has been used to explain the price of diamond. But the conclusion is, among the different variables that we are having, weight is the main variable that influences the price of the model. Okay. So in case that is clear, I think that is the part I wanted to explain further. And you know, you can keep adding variables and reducing variables. You can go ahead and do a confidence interval by using the conf command. You can even put the level that I want at 95%, I want at 90%, I want at, usually it's 99, 90, and then 95, but the commonly one used is the 95%. Alternatively, in case you want to run a linear regression model, I'm just explaining this command for you, and then I'll end there for Professor Susan to start. Sometimes you can also, alternatively, if you're seeing my screen very well, I said, okay, let me rename my model. In case I call this model 3, that is the object that I want, I can change it to anything. I bring in the linear model command, which is LM. I type my regression. Sorry, I type my dependent variable, which is price. And I say price is a function, then I put a dot. That dot means all the variables within consider all the variables within my model. I might not want to type weight, length, width, depth, and so on. The moment I put a dot, R automatically picks all the variables within your model. You indicate your data, and then you run. I'm going to ask in the chat if that is very okay. Okay. Yes. Prof. Susan, I think I've done a good job. Yeah, because participants are saying that it is okay and very understandable. Yes, I'm going to send the updated script in the chat. Now, this time around, I take the opportunity to welcome Professor Susan to move us further. Thank you so much. Yeah. XP lab 1 in the chat.
Good morning, participants. I'll take this opportunity to thank Dr. Helen for taking you through multiple regression. There is a question which is popping out among your questions, and one of you is asking that weight is a function of length, width, and the other variable. And in multiple regression, you can find out whether weight is correlated with other variables. And if it is true, then there is what they call variance inflation factor. You can run your regression model and ask for a variance inflation factor and see which one is really inflating the parameters, sort of like affecting the parameters. So in that case, if we find that we have weight, length, and depth, and we find that adding weight and depth does not significantly improve the model, then we can remove them from the model. Because when we are doing multiple regression, we need a simple model. It's cheaper to collect data, and it is also easier to interpret. So for that case, somebody was asking how to deal with weight being a function of length and diameter and depth. You can keep assessing the effect of removing other variables from the parameters of the original model. But as you can see, the R squared, when we had weight alone, the R squared was 85. point something. And when we added length and depth and diameter, there was just an improvement of 0.01% in the variability explained in price. So that shows you that actually adding those variables do not improve the capacity of the model to predict price. So we can always remove them. But this example was brought for you to know how to deal with multiple regression. Okay, thank you very much. Now we are going to go to another thing called experimental design. Now we are going to look at analysis of data from experimental design. We are going to first of all look at some theories. So let me share. Okay, let me share experimental design. Has it come up? Okay, so we'll have a little bit of theory maybe for 30 minutes. Then we go to the R script. And I believe that all of you got these notes. We sent them last evening after the lecture yesterday. We sent out these notes. We sent out 3 data sets and a script. So hopefully you've gotten them. But if you've not gotten them, Dr. Helen will help me to post them in the chat. You can pick them in the chat or Q&A. So we'll briefly talk about experimental studies. An experiment is where a researcher changes at least one of the variables being studied and observes the effect of that variable on another, and then records the action. Okay. So when you're planning an experiment, you need to have a purpose. I talked about this of the experiment. You need to have specific objectives. We need to know what questions are we answering. We need to identify the population to be considered. For example, if we look at our example of diamond, the population we are looking at are the buyers, the ones who are going to buy diamond. We want to bring diamond of high quality. So we are looking at the population's wants. We are looking at what they need. And if we are going to be in the business of diamond, then we need to bring diamond which is really of good quality and then gives us a profit at the end of the day. So the objective is to sell our diamond and make maximum profit. So as you plan an experiment, you need to specify hypotheses and the parameters required to answer the research objectives. Hypothesis, I know we've already mentioned this. We have 2 types of hypothesis. We have the null hypothesis and the alternative hypothesis. Normally, the null hypothesis is a hypothesis of no difference. For example, there is no difference in the growth of the species when we looked at yesterday the forestry data. So we find that the average growth rate for species A is similar to B, similar to C, and similar to D. And the alternative is that at least one of the average growth mean is different. At least one of the average growth rate is different. Okay? The parameters in that case you're looking at is identifying the species and then growth. We also other parameters. We also can look at diameter. We can look at the color of leaves, etc. So long as they are going to answer your research questions, and your research questions are related to your objectives. So what variables are being collected? So we also look at things like still species. We look at the growth, which is a function of diameter and height. So you have to measure height, you have to measure diameter, you have to measure basal area of the trees before we can now compute our growth. What is the experimental unit? This is really very important for you to be able to identify an experimental unit. When we were introducing experimental design, we said where the treatment is applied is an experimental unit. Now, if you understand what an experimental unit is, I have a scenario which I want us to share. Let me just stop sharing this and share that example which I learned from my colleague. Very interesting example. Okay, so here we are. So I want to share this. Is there? Okay, so I have here a question for us to share and understand what an experimental unit is. Okay, suppose the effect of varieties of fish food is to be investigated on weight gain in some species of fish. The food is placed in the water tank containing the fish. The response is the increase in weight of the fish. What is the experimental unit? I want us to use the chart and answer the question. Let me read it again. Suppose the effect of varieties of fish food is to be investigated. So our treatment is variety of fish food. And we are looking at weight gain in some fish species. The food is placed in the water tanks containing the fish. The response is increase in weight of fish. What is the experimental unit? So can we have some answers in the chat? Let me see. I'm going to open the chat. Okay, very interesting. They are saying the experimental unit is the fish, the food, the water tank, varieties. Wow. Interesting, isn't it? We said the experimental unit is where we apply the treatment. And I can see fish, food, fish species, fish pond, water tank. How do you measure the weight of the fish? That's not my question. My question is, what is the experimental unit? First of all, answer my question, then I'll answer yours. Okay, let's answer this question and let's understand. Thank you so much for the response. So we are saying that we want to investigate the effect of varieties of fish on weight gain of fish. The food is placed in the water tanks containing the fish. What is the experimental unit? And the response is increase in fish weight. So in this case, the treatment is the varieties of fish food. We place it in the container. So now here, the container becomes the experimental unit, irrespective of how many fish there are in the water tank. So the water tank, where the food is being placed, becomes our experimental unit. Then if we want to measure the weight gain, we will first of all measure the initial weight of the fish before we put in the food. How do we measure? You know that it is possible to measure the fish weight. We shall go capture the fish, weigh them, put them back in the water tank. Okay? If you've watched, I think it is NetGeo World, I always see people looking at the sharks. They capture the sharks, they weigh the length, they measure the length, their weight, and place it back. So that's what we can do. We pick the fish weight and then put it back in the water tank, and then put the variety of fish food. After 1 week, we measure the weight gain. Okay, but the most important thing here to learn is where you put the treatment becomes your experimental unit. Okay, now what if I change the scenario? Let me see whether it is clear. How about if the scenario is that assuming the experimenter took the fish in the hand and placed the food in the mouth of the fish, and then what would be the experimental unit? So we change the scenario. We decide that for us, we want to feed the fish. We don't want to put the food in the water tank. Let's have the answers in the chat. What is the experimental unit in the second scenario where the food is put directly in the mouth of the fish? You capture the fish, feed it. Let's see in the chat the answers. Okay, some people are saying fish, the hand, interesting. The fish itself, amount of food. Wow, okay. Okay. Okay, fish mouth, hand. Okay, thank you so much. Okay, so we said where the treatment is placed becomes the experimental unit. So the hand is holding the fish, and we are putting the variety of fish food in the fish. So the fish now becomes the experimental unit. Are we together? Is that clear? You can see the difference. The other time we had the water tank. This time we are placing our food in the fish mouth. So now the fish becomes the experimental unit. After 1 week, we are going to capture that fish and weigh it. How will we identify? We will label them. As soon as you capture the fish, you label them with a tag. You tag them, feed them, release them. Then after 1 week, you capture them, and then again you weigh the fish. So that is the difference in the two scenarios. So where we place our food, our treatment becomes the experimental unit. So in terms of crops, sometimes if we are just spraying the crops, we can decide to say the crop becomes the experimental unit or the plot. If we are looking at fertilizers, then the plot where we are putting the fertilizer becomes the experimental unit. So hopefully that is clear. Let me see some some reactions in the chat. That's interesting. Okay. So is that clear? Somebody is saying, can you explain it again? Okay. Okay, so to bring those other people are saying that I explain it again, we are saying that if you're going to perform an experiment and you're laying down your experiment, you want to identify the experimental unit. Where the treatment is going to be applied becomes your experimental unit. So if in terms of crops, we are looking at the different levels of nitrogen and how it affects crop yield. So what we are going to do, if we have 24 plots and we have 4 levels of nitrogen, 0 nitrogen means that we are not going to apply anything, maybe 5 grams, 10 grams, and then 15 grams of nitrogen. So we are going to get 0 grams of nitrogen, apply them to 6 plots, because remember I've given an example that the number of plots is 24. So meaning that each of these levels is replicated 6 times. Then we are going to get 5 grams of nitrogen, apply them to the plot, 6 plots. So in this case, the plot becomes your experimental unit. Okay. Then after that, when the crops grow and we want to measure the yield, we can measure yield in terms of the weight of the cob or number of cobs, if we are talking about maize or corn. So when we go to the plot, remember there is what we call edge effect of the plot. So we measure off a small distance from the edge of the plot and then measure the middle part. We harvest the cobs from those plants, count them, and then weigh them. So for plot 1 where we didn't apply nitrogen, we will record the weight. But the experimental unit is the whole plot. Okay. I hope that is clear. Let me see in the chat before we go to another thing. Helen, did you pick that question? Is the feeding what? Okay, okay. There's a comment that came in about feeding people. Let's talk about babies. Assuming that we have a new baby feed that has been formulated by one of our students, and we want to test it on the nursery going, let's say kindergarten students. So what we are going to do is that the children will become our experimental unit. So each child in the morning is given breakfast, and that breakfast is made up of different quantities of that food. So in that case, the baby, initial weight of the baby is measured, and other things like height, color of the skin, any disease, all those are recorded. And after 1 week, we start measuring the weight of that child. So in that case, the child becomes the experimental unit because the child is receiving the baby food. Now, for you to find out whether there is an impact, you can have some children who are given maybe just maize porridge without mixing it with that new baby feed. But still what we are saying is that the child becomes the experimental unit because your treatment is the baby feed or the new diet that you've come up with. If we are looking at animals and we have a new feed that we've formulated, and it is indicated that it increases the milk yield, the animals are going to become the experimental unit. So you're going to place your food in a trough, and then the animals will eat that food. You weigh them initially because you do not want to guess whether they've increased in weight or not. So you make sure you weigh them before you give them the food, and afterwards you give them that food. So that is about the experimental unit. And let's go to something else. There are 2 questions here. Is there an effect of the experimental unit onto the fish? If the fish is fed directly, and if the fish food is put in the tank? Of course, there would be an effect because here the fish is given the exact amount he's supposed to receive in a day by feeding them directly. And when you put it in the tank, There are some fish which are aggressive, even if they are of the same species. So they'll be eating more than the others. Yeah, that is natural, even if it's human beings. If we are given food on the same plate, you see somebody eating faster than the others. So they will gain more weight than the others. Okay, let me stop sharing this and move on to something else. Okay, the other thing are factor levels. Those ones we've been talking about them. I've already given an example of nitrogen. If nitrogen is our treatment, it has 4 levels, 4 factor levels. For example, 0 grams of nitrogen, 5 grams of nitrogen, 10 grams, and 15 grams. Those are the levels. But sometimes you find that the factor is types of fertilizer. So you have nitrogen-based fertilizer, then you have phosphorus, then you have potassium, etc., whatever you want to look at. So the factor levels can be qualitative or quantitative. Okay. For example, in the example of forestry, our factor species has A, B, C, D. So they can be qualitative or quantitative. So after identifying the experimental unit, you need to find out the variability within the experimental unit and find out whether you require blocking. So if you're going to perform your experiment in, for example, if let's say we are going to Benin or Nigeria, or we are going to Rwanda or Kenya and want to perform an experiment on one of the farmers' field. So the first thing we go in, we observe the color of the vegetation on the farmer's field. If there are no differences in color of vegetation, then we have to do soil sampling. That is what we call a pilot study. Before you go to perform an experiment, you have to do a pilot study to know whether there is variability. So we'll go in and pick some soil samples, take them to the lab to assess the amount of organic matter. So if we find that the organic matter is within the same range, the values are not so different from the other, then we know the field is homogeneous. The variability is homogeneous, but it is very rarely occurs in nature that you find a field which is homogeneous, because soil factors vary a lot in a short distance. So you have to be careful when you're dealing with soil sampling. Okay, so if you find that the experimental units are variable, there are differences in variability. What I mean by variability is that the values of the observed values are so different from the mean, then we need to block according to variability. Sometimes we can have a slope gradient. So we take the altitude and find out whether it is uniform, it is a flat ground or not. If it's not a flat ground, then we can use altitude as our blocking factor. We also have to look at the constraints when we are planning for an experiment: space, time, labor and amount, and skill. So if you are not grounded in experimental design, then you need to teach yourself if you do not have somebody to teach you, or you get that person who knows about experimental design and learn about the experimental design, because it's not good for you to perform an experiment when you do not have knowledge about experiments. Okay. Somebody is saying, what is blocking and how is it done? The other time we talked about blocking. We even gave an example that in case you are on a hilly ground, then we take altitude to be our blocking factor. So let me move to the whiteboard and demonstrate that. So I want to find out, I'll stop this, and then this is the whiteboard around there. Okay. So I'm assuming that your area is, we will use this for ease of demonstration. So your area is like that. Is that clear? Okay. So if this is your area and you want to perform your experiment along this hill, we are going to divide our hill according to altitude. We also know that as you slope down, the fertility of the soil increases. It's more fertile in the bottom than on top. So we are going to block according to the slope gradient. So we will measure the slope gradient and block. So we expect that this area has similar slope gradient. Then we will also block here. So we expect that this part here also has the same slope gradient. We also block here, and we know that this area here has similar slope gradient, and also the bottom has similar slope gradient. So you can see I'm using different symbols to indicate that this is uniform, this is also uniform, but if you remove the blocking, then we find that they are heterogeneous. So after this, we now form our plots. Remember that these are our blocks. Block 1, block 2, block 3, and 4 are our blocks. I'm also going to write this side. This is block 1, this is 2, this is 3, and this is 4. So those are the blocks. So we are going to perform an experiment here. We are supposed to grow our corn or maize here, and we are applying 4 levels of fertilizer. So we are going to divide the area into 4. So we have our plots going like that. We also say that once you identify the pattern of variation which is going downwards, we place our blocks perpendicular to the variation. So the blocks are placed perpendicular to the variation to maximize the variation within each block. So once we've laid out our blocks, we now divide them into plots. After that, then we apply our treatments randomly. So we randomize the experimental units and then apply our treatments. So we have 0, 5 grams, 10 grams, and 15. So like that, even within block 2, get different randomization for the treatments. So I'm just placing this, but I'm assuming that they've been randomized. Okay? So then you plant the crops and assess the crops. So that is blocking. Okay? So what is... Okay, we are going also to talk about replication. So let's go ahead, and when time comes for talking about replication, we will know about it. Okay. Okay, so that is blocking. So after planning for an experiment, there are basic concepts of experimental design that we need to know. We need to know about replication, we need to know about randomization and blocking. We've already talked about blocking, and we are going to talk about the importance of blocking. We also need to know about the basic experimental design. There are so many. And we also need to know about the treatment structures. We are going to talk about them and the assumptions underlying the analysis of variance and treatment comparisons. Okay. So in designing a good experiment, we need to know the experimental unit. We've talked about them. We identify the units and also the pattern of variation. We've already talked about it. And then look at the design, the allocation of treatments to the experimental units. So if we are in a greenhouse, because we are able to control the background information of variability, then we lay up a complete randomized design. So in that case, we randomize our treatments to the experimental units, okay, depending on the number of replicates. So we've already talked about what an experimental unit is, and I think I'll not repeat this. So let me just go to the treatment. We also talked about the response. We've also talked about it, but the response can be quantitative or qualitative. In the example of crops, we can look at the color of crops. When you are a farmer and you plant maize, the first thing that strikes you is the color of the crop. If it's dark green, you know that the crop is doing well. But if it's light green, you know there's something missing, and then you need to bring foliar fertilizer and add. So even when you're doing an experiment, you pay attention to the color of crops and record during the experiment. As you record the weight, you record also the color. At 1 week, the maize or corn had changed color from green to yellow. And you will also know why there was a change in color. Quantitative response are those ones where we measure, for example, weight, height, and diameter. The subsampling, this one I'm going to mention in passing because some people confuse subsampling for replication. So assuming we have our experiment, which I have just talked about, and then after laying the plots, we put in 0 grams of nitrogen, 5 grams of nitrogen, and 10 grams of nitrogen. We split them into 2, and then plant 2 varieties, corn 1 and corn 2. That is not replication. So if I can go back to the whiteboard again and just show you briefly what I'm saying. So I'm going to use one plot. So assuming this is one experimental unit, we applied 0 grams of nitrogen, but then we split it and grow corn 1 and corn 2. So our objective is to find out how those 2 types of corn respond to the different levels of nitrogen. So by splitting your original plot into 2 does not mean that you've replicated. You've not done any replicates. You can't see the whiteboard. Okay, let me try one thing. Let me try to switch off. Is it visible? Is it better? Yes. Okay. Is the whiteboard better? Is it more visible? Okay. So this is the main plot. We are talking about subplot, subsampling, or splitting the plot. So if this is the original plot, you've applied 0 grams of nitrogen, but you have 2 varieties of corn. So we are going to split it, and on this side we plant corn 1, on the other side we plant corn 2. So if we do that, we do not assume that we replicated. No, we need to create another plot with 0 grams of nitrogen and then split them. Then we have corn 2 and corn 1. We would have now replicated. So this is now what we call replication. Okay? And this is called subsampling or splitting the plot. Okay, so that's what I wanted to make clear. I hope there's no question. Let me check the chat. Okay. Okay, so let me go back and then we talk about subsampling. So subsampling occurs in vegetation surveys, and after researchers have collected data on many plots, they say they replicated 30 times, which is not true. When you do a survey, you're not replicating. Each plot is unique in its own self. So if you do the same thing in another area, for example, you go in another site of similar conditions and you do the same experiment, then you would have done some replication. But remember, you have to put in site as a factor when you're analyzing your data. So measurements are taken on a subsample. I was giving you an example that once you've planted your crops, to avoid edge effects, we measure a small distance from the edge of the plot inside where your crops were planted and demarcate that area on all edges of the crop and then start measuring. So you would have eliminated the edge effects. Now, there are what we call repeated measurements or correlated units. Now, in our example, which I've just demonstrated, assuming that we measure the height, the increment in height over time, because we are measuring height on the same experimental unit over time, those measurements are not independent. When you measure in week 1, week 2, week 3, they are not independent, they are correlated. And we call those repeated measurements. And they have a specific way you handle them, but we'll not talk about that today. Okay? So let's go ahead. There are also what we call lacking variables. Those variables which you are not sure of, you're not aware of them, but they affect the outcome of an experiment. Okay, so you have to be aware of those factors. For example, if you go in the field and you do not use blocking, so what you're going to do is you're going to go in, lay your plots and apply your 0 grams of nitrogen, 5 grams and 10 grams and plant your corn and then wait after some 3 months and measure the yield. Now, because you didn't control for differences in the soil variability, it is going to affect your results, but you cannot actually explain that it is the soil fertility. So those are called confounding variables. Other people call them lacking variables. So you need to control them either by blocking or you introduce them in your study as a factor. Another example is that if you're dealing with feeding, if you do not take the initial weight of the children, of the animals, then you're going to be confused whether there has been an improvement or not. So that one becomes also a variable that is confounding your results, and you should take care of it in the experiment. So what is an effect? We normally hear of treatment effect, etc. An effect is the change in the response that is caused by the change in another factor or independent variable. So if we apply 0 grams of nitrogen to our corn, we will get a certain yield A. And if we apply 5 grams, we've changed our factor to 5 grams, it is going to have an effect on the yield of corn. So that change is what we call an effect. And in the analysis of variance, we are looking at that effect. Is it significant? Has the treatment had an impact on the response? That is what we assess. But there are also what we call fixed effect and random effect. I think you've heard of those ones. Now, fixed effects, when we are dealing with fixed effects in experiments, effects are called fixed when the experimenter had a certain number of treatments and used all of them in the experiment and is assessing them. So we call it a fixed factor. But after it has had an effect on the response, it produces a fixed effect. Now, random effect. An effect becomes random if you have a population of factors. For example, you have 10 blocks, but you randomly select 2. to put in your experiment. That is where you're going to perform your experiment. Another example is you have 4 locations, 4 sites, and then you randomly select 2. That becomes a random factor, and it produces a random effect in your analysis. Okay. So we are going to briefly talk about the principles. Some of the things I'll leave you, they are very clearly explained in the notes. So I will brush over them very fast so that we have time to look at R. How do you analyze experimental design using R? Okay. So principles of experimental design. We have replication. The number of times treatments appear in an experimental setting is replication. So if you have treatments A, B, C, D, and they are appearing 6 times, that is what we call replication. Why do we replicate? To be able to measure the experimental error, which is the basis for determining the differences in the experiment, for determining the effect. If we do not replicate, we cannot also compute the standard deviation. Because you remember, the denominator of standard deviation of a particular treatment is n-1 or t-1. That n-1 is due to replication. So if you have one treatment in one plot, you've not replicated, the denominator in standard deviation is going to be 0, because 1 minus 1 is equal to 0. Okay? So we replicate to improve our precision and to be able to estimate the experimental error in our design, which is used to test the treatment effects. How many replicates? There are factors which determine the replicates. The pattern and magnitude of variability among the study area, the size of difference to be detected. This comes from literature. Size of difference to be detected comes from literature, because many people must have performed the experiment you're going to do, if not similar or somehow related. So you have to read literature and get the size of the difference to be detected. And then the required significance level. And normally for agriculture, environment, forestry, food science, our significance level we set is 5%. But when you set 5%, it also determines the number of replicates you are going to use. Remember, the significance level is the amount of error you are accepting in your conclusions. For example, if you produce a feed, a unique animal feed, and you give it to 100 cows, and we've used a 5% significance level, you're saying that you're 95% confident that the new feed will improve the weight of the animals, but you're 5% wrong. That is the significance level. Because the significance level is the probability that the null hypothesis is assumed to be correct. And remember, our null is saying that there are no effects, there are no treatment effects. That means the treatment you've produced does not actually increase the weight of the animals. So remember, when you're choosing your significance level, that it is the amount of error you're making in your conclusions. That's why in the medical field, the significance level is reduced to a minimal level or a minimal probability to avoid, getting casualties, to avoid people getting sick or dying as a result of the medication that you've produced. Okay? Okay, let me check the chat. I can see that there's a lot of response. Prof, can blocking also be done in lab experiment? Yes, blocking can be done in lab experiment. If, for example, your lab is stationed in such a way that the sun moves over the lab, across the lab, so you can decide to take side the where it rises from and where it sets to be your blocking factor. if you think it's going to affect your results. Okay. What is interaction effect? We will look at that in the factorial treatment structure, so we will cover that. Do you have replication in complete randomized design? Yes. In our example of forestry data, we had 4 species, but our experimental units are 24. Meaning that if we divide 24 by 4, each species is replicated 6 times. So yes, it is true. What is the difference between replication and repetition? Okay, now that is English, I think. Replication, we've said it's the number of times a treatment appears in the experimental units. Repetition may not be replication. Okay. Replication is used in experiments. Somebody is answering, thank you. And what about repetition? You can give an. Okay, repetition. For example, if you say you've not understood what blocking is and I repeat myself, that is repetition. Okay. Okay, thank you. Any other comment that I've not attempted or have not attended to? Between what? Okay. Difference between dependent and independent. Okay. My colleague, Dr. Helen, talked about independent and dependent variable. In the regression setting, we assume that the independent variable is measured with minimal error. And the independent variable is measured with minimal error, and the dependent is the one which varies a lot as we put in the dependent variable. So in this case, the independent variable in terms of experiment is the treatment. The independent variable is the treatment. You will measure 0 grams of nitrogen with minimal error, but the yield will be subjected to many factors coming from the soil, coming from the environment, the rainfall, and then the experimenter yourself. So that's why yield becomes variable. There's a lot of variation in yield, which is going to be explained either by the treatment or other factors. So the difference between independent and independent is that independent is measured with minimal error or has minimal error, and the dependent has a lot of variability. Okay. What is the difference between randomization or random? Let me talk about random factors. You have a pool of factors and then randomly select a few. Then fixed factors, you have 4 factors, and that's what your resources can afford, and that's what you put in your experiment. Now, after performing the experiment, the effect that those factors cause are called effects. For example, fixed factors will cause a fixed effect, while the random factors will cause a random effects. And they also determine the type of analysis you're going to perform, especially the random factors. Okay. Okay, if that is okay, let me see in the chat. Difference between replication and blocking. Kindly include sessions while running. What is it? Okay, difference between blocking and replication. Replication and blocking are principles of experimental design. And we said blocking is used if you know that there is variability between the experimental units, and you want to control that variability before you perform an experiment. And then when replication is the number of times a treatment appears in the experimental setting or study. Okay, replication is used to measure experimental error, while blocking controls the background variability and it improves the precision of the experiment. Okay. So how many replicates? There is an example, but I want to give you that as something that you can do in your free time. Because in determining the number of replicates, we need to know the detected difference. We need to know the size of the significance level, and then we determine the number of replicates. So I'm going to send the worked example for you in the notes, and you will have it. So let's go on randomization. Randomization ensures that the treatments have equal chance of being selected and allocated to an experimental unit. And we know that under all inferential statistics, we assume that the treatments have been randomly assigned to the experimental units. We assume that when we go to do our surveys, we've randomized the households so that we are able to perform our inferential statistics. So if you do randomization, then that assumption is valid, okay, under statistical inference. And also it helps us to avoid experimental bias, because you might be interested in a particular crop, for example, sweet potato crop, which you've tested and you feel it is the best and you want to promote it to the farmers. So you end up growing it in the best soil so that it performs better, and then you promote it. So when you have such bias, by randomization, such bias is avoided, okay? Because then if you randomize, you can't change the random nature in the field and you say, no, I'm going to look for fertile areas where I place my treatment A, which is the best, okay? We've talked about blocking, and you can now read that treatment structure. So sometimes we have factors with levels. For example, we can have sources of fertilizer such as, I've put in DAP, but they are abbreviations. CAN is calcium, aluminium, and nitrogen. I think DAP is aluminium, phosphorus, and dye something. I forget my agriculture knowledge, and then manure. So we find that those sources of fertilizers have different levels. You want to find out which is the best combination of those factors that gives us the highest yield. So when we have only the factors without levels, for example, we have fertilizer as our factor, and we have 3 types of fertilizer, DAP, CAN, manure, and we are looking at those, if the effect of DAP, CAN, manure on the crop, then that is called one-way treatment structure. Now, if we have fish species and different feeding regime, that becomes a two-way treatment structure. But sometimes you can have a fertilizer called CAN, which consists of calcium, aluminium, and nitrogen, and then manure, but different concentrations. So for example, for CAN, you have 3 concentrations, and manure, you have 4 concentrations. So that becomes a 3/4 factorial treatment structure. And you have to know whether you have different levels of a fertilizer or not before you perform your experiment. And if that is the case, each level of a factor appears in each factor. For example, if you have manure and CAN, then in plot 1, we are going to have 0 CAN and 0 manure appearing together. Then we have another plot 2, we will have 0 CAN and 10 grams of manure. So the factors appear together, and the combination of factors now become the treatments. So this is about the treatment structure in experimental design. Or somebody's telling me it's called calcium nitrate. Thank you so much. I've forgotten my... Okay, let's go ahead. So we are going to go to experimental design and analysis. We will briefly talk about the types of design. And because of time, we cannot cover all of them. We know that there are several designs, but even the information, the literature explaining those designs is available. If I don't forget, I would like to give you the sources where all these designs are simply and well explained. You can pick the information easily and use it in your design, or even know what type of design you have. So we will look at what we can in the required time. So the first design we are looking at, we've been already mentioning it. It's called complete randomized design. It's used if we have homogeneous experimental material or the background conditions are controlled. So if that is the case, then we assign the treatments randomly to the experimental units. Each experimental unit has equal chance of receiving one treatment, okay? So because of randomization, we give them the same probability to receive a treatment. So in complete randomized design, we are not worried of blocking because now the variability is similar throughout the experimental study, and we are not now worried about the effect of the treatment on the response, which we are interested in, okay? Now also remember that the type of design goes hand in hand with your objective, and it is answering your problem. So if you're talking about a certain area which requires blocking and you're now saying you're going to use a CRD, then you're not going to answer your questions or your objectives. So this is something I picked from this study here. The source is included. It's a complete randomized design. You can see that we have 13 experimental units. There are 15. We have 15 experimental units. Where I see the arrows pointing down are the experimental units, and T1 is treatment 1. They've been randomly assigned. So we have T4, T3, T1, etc. And from this experiment, what is the number of replicates? Can we have an answer in the chat? How many replicates do we have? Okay, I can see 4, thank you, that is great. I'm now very, very happy because it shows that you are understanding what we are talking about. There are 4 replicates, yes, thank you so much. How many treatments do we have? Okay, 4 treatments, thank you. We have 4 treatments and 16 experimental units. Okay, great, excellent, thank you so much. So we have 16 experimental units and we have 4 treatments replicated 4 times. So you can see that in this example, they are showing us that this arrow, if you see this first arrow, is showing that tau I is the treatment effect and epsilon is the experimental error, and this is the observation error, which is fused within the experimental error. So this is the model briefly that you could have. And the analysis of variance table, which comes up, looks like what you see here. We have the treatments, that is the source of variation, the unexplained variation, which is experimental error plus observational error, and the total variation, which is not shown. So the degrees of freedom here, for treatments, it is the number of treatments minus 1. So here we have 4 minus 1 gives us 3. Now error, it is the number of experimental units minus the number of treatments. So we have 16 minus 4 treatments gives us 12. And the total, which is not shown, the total variation, if you add 3 and 12 gives us 15. But there's this formula which is total number of experimental units minus 1 gives us the total degrees of freedom. Okay, you can see that here, experimental error. We talked about replication and we said that if we replicate, we are able to estimate the experimental error. Now, assuming that we had not replicated, we had 4 experimental units, 4 treatments, we would have, what would be the value of the experimental error? Let me see the answer in the chat. Assuming we didn't replicate, what would be the degrees of freedom for experimental error? Assuming we didn't replicate. I said, yes, I can see one answer which is correct. 2, 3, 4, 5, 6. If we did not replicate, okay. Okay, thank you very much. So if we did not replicate and we are assuming that these other units are not there, that means we are going to have only 4, T1, T2, T3, and T4. And when we go to write our analysis of variance table, the treatment degrees of freedom is 4 minus 1. So we get 3. Now, experimental error degrees of freedom is the total number of experimental units minus the number of treatments. So we have 4 experimental units minus 4 gives us 0. So if we don't replicate, we are not able to actually analyze our data. Because when we are analyzing data, the experimental error is what you use to determine whether there is a treatment effect. Are we together? Is that clear? Okay, so we'll have 0 error degrees of freedom. Somebody is saying, what is degrees of freedom? Degrees of freedom is the amount of information which is free from constraint. What is a constraint? Free from a problem. For example, if we have 5 observations, and we have 5 observations, we have, let's say, you can write in your notes, we have 5 observations, we have 20, we have 30, we have 40, and 50, but we don't know the last observation. And we are given that the mean of those observations is 40. Let me say 60, sorry. So I'm giving an example to explain degrees of freedom. Assuming we have 5 observations, 20, 30, 40, 50, but the last one, the 5th one is not known, but the mean is 60. Okay? We are told that the mean is 60, and we are told to estimate the last observation. So in this example, we can freely guess the first 4 observations, but the 5th observation, we need extra information, which is the mean or the total. So the degrees of freedom is the amount of information that is free from constraint, which we can freely guess. But the 5th observation, we need to know the value of the mean. That is a constraint, because then you need to calculate the mean, or we need to know the total. Are we together? So if we have the mean, then we can have the total. So if the mean is 60 times 5, that means that the total number of observations is going to be 300. If we have 300 as our total, we add up all these 4 observations. 20 plus 30 is 50, plus 40 is 90, plus 50 is 104. 40 minus 300 gives us the last observation. You see the hassle you've gone through? So the 4 observations are free from constraint. They are your degrees of freedom. So even the treatments, 4 minus 1, you can easily guess your 3 treatments, but the last one, you must know the treatment. You must know the mean. You must know the total for you to be able to guess the 4th one. So that is degrees of freedom. The information free from constraint. Why do we say minus 1? Because we use that information to compute the mean. In all the formulas that you see here, the mean is very important. When we are estimating the treatment effect, things we are not going through the math, but if we are going to calculate the sums of squares for for treatment, we need the grand mean. We add up all the observations and divide by 16, gives us the grand mean, which we subtract from all the others. So the mean is very important, and because you're using some information to calculate the mean, that's why we are now subtracting that one. And when we come here to error, we have 4 parameters we are estimating: the tau 1, tau 2, tau 3, and tau 4. Those parameters are taking up 4 observations or 4 information. That's why we have experimental error degrees of freedom being n minus 4. In the first case, the mean is also called a parameter. You remember that. Okay. In the error part of it also, the 4 affects the tau 1. Tau is a Greek letter. We are using it to signify our treatment effect. So we have treatment effect 1, that is tau 1, treatment effect 2, treatment effect 3, treatment effect 4. So we have to estimate those and subtract from 16 observation to get our error degrees of freedom. Okay, let me see in the chart. If that is okay, we move to the next thing. Okay, thank you, thank you. Okay, great. Okay, let me go to the next thing. So this is the model which we can always look at it or look through at your free time. We have Yij, observations from the jth experimental unit of the ith treatment. Mu is the overall mean for all the observed response. Tau I, tau is a Greek letter. It is the effect of the ith treatment on the response. And E is epsilon, which is the experimental error. On each treatment, we have an experimental error. We can calculate it. You remember the residual which we talked about in regression? It is the same here. So we call it unexplained variation. We call it experimental error. We call it epsilon. So if we want to make E the subject, we will get the observed minus the fitted, which is mu plus tau I, which is similar to regression. So actually, under treatment experimental design, mu and tau I is our intercept and slope in regression. So mu is our intercept and tau is our slope. So that's how we have a relationship there with the regression. But here, our independent variable is categorical. Meanwhile, in regression, the independent variable is continuous. Okay, so let's go on. This is an example. I think I've given you these examples. You already know. I know you are good now. You know how to determine the experimental units. Let's move on to something else. I have an example here. I want us to talk about analysis of variance. Analysis of variance, which is abbreviated as Anova, is a statistical technique used to compare more than 2 population means by isolating the sources of variability. So Anova divides the total variability into variation between the treatment or treatment variation, and then within treatment variation, which is called residual error unexplained variation. Okay, so that's the analysis of variance. Now I have an example here, which we've been using actually in our R, and we talked about it. So want to compare the growth of 4 species of mahogany. They are replicated 6 times. And the questions are, state the hypothesis being investigated, state the method suitable for analyzing the data, and give your conclusion. So this is just to help you when you are writing your proposal. You need to know the hypothesis, you need to know the method of analysis, and what conclusions you expect to have, although they are not correct ones. So when you're writing your proposal, you must know your hypothesis, you must know the analysis you're going to perform on your data, even before you collect the data. Do not do a post-mortem of your data. You go to collect data, and then you think of how to analyze it. You're going to face problems, my dear. Even if you bring it to a statistician, he or she is going to get the same problem because there are some factors we've not controlled. Remember, the type of analysis goes hand in hand with the design. It goes hand in hand with the objective. So all those should be related. When you're writing your proposal, you should have a sequence of events happening in your proposal. And when somebody reads it, they will understand and be able to give you, if you're looking for funds, you'll be able to get the funds very fast. If it is your defense, you will defend successfully because you know what you're talking about. Research is cyclic. One section cannot be separated from the other. The topic is related to the problem. The problem, we get our objectives from the problem, and then the methodology is related to the objectives, and then the analysis is related to the method and the objectives. So when you're coming to that type of to part of analysis, you actually analyze your data per objective. That is the easiest way to simplify problems of analysis. So get objective one, look at it, look at the proposal, what you had suggested. Does it still suit the data? You can always modify because we do not know what is happening in the field. But most cases, it's not different, especially for experimental design. If you've set up a complete randomized design, you cannot change goalposts and say now it's a block design. You see what I mean? So you don't beat about the bush when it comes to statistics. You're specific, okay? So let's go ahead. So hypothesis, we are going to look at it. This is the data for you in case you want to use for practice. The hypothesis in statistical terms is that mu A is equal to mu B is equal to mu C is equal to mu D. Please don't state it the way you sit here. It is said that do as I what? Do as I say, not as I do. So what I've shown there, don't do as I do. Please write it in terms of your research question and objective. So in terms of the question that we had, there is no difference, or there is no treatment effect, or there is no species effect on the growth. Or let me restate it. The average growth of treatment A is equal to treatment B is equal to treatment C is equal to treatment C. That is how it is stated. But when you're writing in your thesis, in your project, then it should be different. You should use better English than mine. We can say that there is no treatment effect, or the average growth is not different for the different treatments. Then the alternatives that not all means are equal, or at least one of the means is different. And the type of analysis we are going to use is called a one-way analysis of variance. Why do I call it one way? We only have one factor, that is species. If we had species and type of vegetation, then that would be called two-way analysis of variance. I want to talk briefly about this analysis, then we go to R and perform the analysis and see whether we are going to get the same output. Now, when you analyze your data with a one-way analysis of variance, you expect to see this analysis of variance table. You will see source of variation, degrees of freedom, sums of square is SS, MS is mean square, this is F value, and this is the probability. Here we have TRT is treatment, so here it should be species. Error, we've already said it is the experimental error, residual, or unexplained variation, and this is the total variation. You can see degrees of freedom now. This is where I want you to pay attention. When you analyze data, the first thing you should check to find out whether your analysis is correct is the degrees of freedom. Do you have the correct treatment degrees of freedom? We said it is number of treatments minus 1. We have 4 treatments minus 1, we get 3. That is correct. Error degrees of freedom. We said it is the total number of experimental units minus the number of treatments. So it is 24 minus 4 gives us 20. That analysis now is correct. We are good to go and interpret the rest of the things. So when it comes to analysis of data, do not cram, understand. Because if you do not understand, then if the computer gives you wrong things, you're going to interpret them the way they are. And if you find a statistician on the panel, then he's going to say this person forged the results, because he will know that there's something wrong with the output. Okay? So always know that the output given to you is correct. So sums of square, there is a formula which we are not going to look at, but mean square here, I can give you a simple formula. It is sums of squares divided by the degrees of freedom. Okay, so you get this value here, divide by 3, you get the mean square. Error mean square is the sums of squares for error, divide by the degrees of freedom for error. So you get the mean square error, and you also get the treatment mean square. The F value is the ratio of the mean square treatment and the error mean square. You get the F ratio. Okay? Now, this error here you see here is the standard deviation of the data. It is the it's the variability, the variance of the data. And the standard deviation is the square root of this value. So this is the variance of the data. If we get a square root, we get the standard deviation. And in most packages, you will see S is equal to a certain value. So that is the value. If you get the square root of 22.8, it gives you a certain value, and it is the standard deviation. And it's what we use to test for the effect of treatment. Now we can see here, because we only have 4 species, we didn't have a pool of species where we randomly selected. We specified only 4 species, and that is the amount of resources we could use in that experiment. Because they are fixed, we call that a fixed effect. Now here we are looking at the effect of treatment. It is fixed. And when we divide by 22.8, it gives us an F value and a corresponding P value. You remember that we said we are going to use our default of 5% to test our hypothesis. And we said 5% is the probability that the null is assumed to be correct. So if we get anything lower than 5%, then we have evidence to reject the null hypothesis and conclude that not all means are equal, or at least one of the means differ. Now that is not all. If you know that not all means are equal, so what? We have to go ahead and find out which mean has the highest mean growth, which mean has the least, and then we make conclusions to the farmers to grow that particular species which is growing very fast. Okay, is that clear? Let me look at the chart. Okay, now P is equal to, somebody says that, does P equal to 0.00 mean that there is evidence against the null? If your significance level is 0.05 and P is less than 0.05, then we have evidence to reject the null hypothesis and conclude that not all means are equal. Okay, then after doing that and we find that not all means are equal, we do what we call pairwise comparisons, or least significant difference. You know, we test the means to find out which means are different from the other. Okay, so here I've printed out the list of means. So we can do different things here. We can present a table of means and talk about their magnitude. We can see that treatment B gives us the highest growth rate and treatment C has the least growth rate. And when we look at the standard deviation, they are within the same range, meaning that the data, and compared to the mean, the data is not so variable. Okay, so we cannot draw what we call error bar, a bar chart with error bars attached. Normally, we use either the standard deviation or the standard error to draw the error bars. And each treatment has its own standard error. So the package will know that I will pick the standard error of A, or you can specify them depending on what statistical package you're using. So now that we are using R, let's go to R. There are some assumptions here, but I think I'll not talk about them. You can read about it. Let's go to R and have a feel of R. How do we analyze data from an experimental setting? So we are going to change goalposts now. Huh? How? Do we what? Oh no. Okay. More answer. You know, in R, what do you do? Okay. Okay, so there we are. So let me open. There's this script we sent you. It's called experimental design.r. That is the extension, but it is the file is called experimental design, and it has been sent. Helen says she has already sent it, I think, in the chat. Thank you, Helen. For experimental design, we are basically concerned with library, learn R, read Excel, read R. So what I do, I'll just do everything. I'll run all my libraries. So because you've opened a new script, you need to run your library. So we run. Now remember, I've added on Agricola, which we talked about yesterday. I'm going to load them because they're already installed. So I'll just click run. It doesn't take a long time. So long as you don't get any red in the console, all these have been installed. And if you want to find out what Agricola is, put help here. So assuming we type help and put in bracket Agricoli, and then enter. Okay, thank you. You see, R has also helped me to put the quotes automatically. So you can see that under here, at the bottom right, we see the description of what Agricola is. It says Agricola is a statistical analysis of experimental design applied especially for field experiments in agriculture and plant breeding. Okay, so now you can actually know what is in Agricola. Even if you put it, you'll know what it does. Okay, you can also use Google to get more important information. But within the PowerPoint, I've also put in the author of Agricola. Okay, and also Dewey. I've put those two authors, so you can download. I cannot share them here, but you can download them and then read. You can read. Okay, zoom screen. Control positive. Can you put on the light? Okay, is that more clear? Okay, let me see in the chat. Is it clear? Okay. Okay. Okay, thank you so much. And thank you, Helen, for more light. Okay, so the first thing we do is to run our library. So you just highlight and run. And when you run a library, we are loading that package, telling R we need to use that package. So the second thing we do is to set our working directorate. If you've not set it, I hadn't set it. So I'm going to session and then set working directorate, choose working directorate, and that is it. So I browse to my folders and click the folder where all my R data is stored. Then I click OK. So below here in the console, you will see the path of your working directorate. So from there, the next thing we are going to do is to import our data set, which is forest.csv. We've been using that data set, so you should have it. So I've already written the import command, which you already have in the script. So just run that command. But if you do not have the command, then you can write it actually. And also here, remember that sometimes I just come and find out whether Agricola really worked. So I rerun, but now I'm not going to rerun the package. So we go ahead. After importing our data, we know we can now find out the structure of the data. These I'm just adding in for your own benefit, but you can type them in. Structure equals forest to know what it has. So if I run that line, we will see in the console, it's saying the data frame has 24 observations and 2 variables. Species is a character and growth is numeric. Now, if it specifies it as a character, we won't be able to use it for analysis, so we convert it to a factor. You can use as factor or you can use factor function. So here species is the name of the object, a sign, or you can put equal, factor, open bracket. Forest is the data set, and then $, we are saying look into forest and pick species. It is what we want you to convert to factor. So I run. The next part is I'm going to run a GLM model, and the GLM model, I'm giving it the name status.anova. You can call it Y, you can call it X, it will still work. So assign it to GLM. GLM is linear model. Growth is the response. It is a function of species. Normally that symbol is called follows, but it can also be interpreted as function of species, comma, and our data is called forest. So we run that line, and we run another line called Anova. Then we get the output. So I'm going to move it up here, and we see the results. So is this analysis of variance table visible? Is it visible so that we can interpret it together? Okay, thank you. And thank you, Helen, for posting the data set. Okay, so let's do the interpretation. We remember that when we did our structure, it said it had 24 observations and 2 variables. One is called species with 4 species, and the other is the growth. So you look at the analysis of variance, it is similar to what I had in my PowerPoint. And it has degrees of freedom for species is 3. And T minus 1, number of treatments minus 1 is 3. Residual is number of experimental units minus the number of treatments, which is 24 minus 4 gives us 20. Sums of squares, there is a formula. So if you go into those statistical books, you will see those formulas. They are very, very simple. Don't run away from formulas. It challenges your brain, and you don't sleep when you're calculating formulas. Okay, it never does when it comes to formulas. Mean square, I said it's the ratio of sums of squares and degrees of freedom. And then F value is the ratio of the mean square for treatment and the mean square for residue. Now, this is an F test, and it has degrees of freedom 3 and 20, because the numerator is mean square treatment. So the corresponding degrees of freedom is 3, and the denominator is mean square error with 20 degrees of freedom. This p-value of 1891 corresponds to a probability of 4.67 times 10 to the power minus. So if you put in those minus, you get 0.000. That's why other packages don't precisely estimate the value, but R gives you actually the exact probability, which is really good. So if we remember our hypothesis, we were saying that the null is that there are no differences in the effect of species on growth. And the alternative is saying that there are differences. At least one of the species has a higher or a lower mean growth. Now the p-value is smaller than 0.05. I have set 0.05 to be my significance level, assumed to be correct is 0.05. The chance that the null is correct is 0.05. So if that chance is reducing because of the calculated probability, which is 0.000, then we have evidence to reject the null and conclude that at least one of the species is different. It has a higher or a lower growth rate. So after that, we now go and print the means and test them. Now, if you find a non-significant treatment effect here, you report it, but don't go ahead and produce the treatment comparisons. Don't do pairwise treatment comparisons because it doesn't make sense. If there's no overall difference, then what are you now testing? Okay? So in the analysis of variance table, if this p-value is big, assuming our p-value was 0.6, that means the chance that the null is correct has increased, meaning we have no evidence against the null. And we conclude that actually there are no differences. But so if there are no differences, don't do treatment pairwise comparisons. But now here, since we have differences, we are going to go ahead and do pairwise treatment comparisons. Is that clear? Can I see in the chat? Okay. Okay, so I'm going to go back to the R script, and I've given you an alternative way of producing the same output using function A or V. So this you can run in your free time. It's going to give you the same results, but let me run it because we use it afterwards. Okay, so let me run this function. So when you run, we are saying that our object space is assigned to A or V, which is an isovariance. Growth is follows species and data is forest. So we run that and we do summary. You see that it is the same output coming up. Now we are going to do our multiple pairwise tests, which some people call post hoc tests. And we are going to look at the least significant difference. And before I do this, we know that there is a hypothesis stated under the least significant difference, which says that if the absolute mean of the difference, for example, if the absolute difference between treatment A and B is greater than the LSD value, then the two treatments are different. I'm going to repeat. If absolute are those straight lines, vertical lines they put across a mathematical expression. If the mean of A minus the mean of B, irrespective of the sign negative or positive, is greater than LSD, the value of LSD, then that difference is significant. Okay? So, but what R does, it actually interprets the results for you and assigns A. So let's see what R does. So in R, we've said the object is LS. LS doesn't have any meaning, it's just the object. And this time I've used equal sign instead of as less than dash. lsd.test. So I want it to perform an lsd.test. You can see it is actually defining what you need to put in and what it will do by default. So it is testing the species. Species is the model, which we did above there. And in that model, we need to look at species. Okay, so let's run that line. And then we print the object. So I am going to move this up. And if you've read some people's articles, you find these A, B, C, L, assigned to the treatment means, okay? Sometimes they put them as superscripts on the treatment means here. Please go to the console and look at the results. Are they clear? Should I go ahead and interpret? Let me see in the chat. Are they clear? Okay. So somebody is saying, is there a difference between analysis of variance, GLM and AOV? There is no difference. You see, the output was similar. So because the output is similar, we go ahead and do our treatment comparisons. And I'm saying the first treatment comparison I'm using is the LSD. Okay. Now we've produced our treatments. They are here, right here. Let me do control positive so that they grow bigger. Okay, there we are. Okay, so you can see I've made them wider by using Control Plus. So if I want to go back to my original sizes of the windows, I'll do Control minus. So we see species A, B, D, A, and C. So we are testing the differences. If we look at B minus D, is there a significant difference? So what R has done, he has assigned letters. And when we look at these letters, means with the same letters are not statistically significantly different. I repeat, means with the same letters are not significantly different. So if we look at the magnitude of A, it is 20.49, and magnitude of C is 19.49. Surely there's no significant difference. So what R has done, it has assigned CC, meaning those two are not different. Now, means with different letters are different. So if we compare B and D, the letters assigned are A and B, meaning they are significantly different. If we look at B and A, the letter is A, small a for B, and C has small c. Because those letters are different, it means that the mean of B is different from the mean of A. The the average growth rate of B is different from the average growth rate of A. When we look at B and C, it is the same thing. The letters are different, attached. These are the letters I'm looking at. And the things I'm talking is what you're going to write in your project. You will copy this, put it in a Word document and name it maybe means of species. Then you come down here and start writing what I'm talking. B has the highest mean growth rate, and it is significantly different from D, C, and A. While D is significantly different from A and C. But A and C are not significantly different. In bracket, table 1. Are we together? Is that okay? Or you want it repeated? Okay. I can see in the chat you're saying it is okay. What does mean? Okay, somebody says repeat for me. We are also going to see an example where we have two letters assigned at the same time. So The next example, we are going to look at that. So don't worry for those saying, what if two letters are on the same mean? So we are going to see that example in the next example. So let's go and look at, so somebody says, I repeat, you're going to write around this result. We are saying that the mean of B is significantly different from D, from A, from C, because the letters are different from A. B is assigned a letter A, and A is different from B, is different from C, and from A. Now, if means have the same letters, similar letters, like you see A and C, those are not significantly different. But if we have different letters, then they are significantly different. Is that clear? Okay. So now let's go to the next section. Now I want to present my data as a bar graph. So I'm going to present the model. LS I said was my model. The next command is I'm using the bar.group to present this information, the same information in a bar chart. So I'll just click run, and it has refused because I made my, so I'll do control positive. So you see I got a red this time. The reason why I'm getting a positive is I made my windows big. So I'm going to run the same thing, and there we are. So let's look at, so I hope you've picked, when you get that error of, is it image, margin is too large, you use control negative to make them almost the same size, and then rerun your model. So let's see what happens. Okay, so you see our graph here. We have A, B, C, D, but instead of putting our letters on top here, we have error bars on top. Okay, there's also another command which I've put in to produce error bars, so you can practice that. But now in that same command, we've drawn our bar graphs and attached error bars. Okay, so as we interpreted the letters, even the error bars, when error bars do not overlap, then those two treatments are significantly different. So you can say A and B are significantly different, but A and C, they overlap, they are not significantly different. This is the same result we are getting even when we saw R allocating those small, let me zoom this out, sorry about that. I want to share the graph. Okay. Okay, participants can now see. Thank you very much. We are saying that if these error bars do not overlap, you can see this one ends here and this one is down here below, so there's no overlap. So the effect, the difference between A and B, significantly different, and B and C are significantly different, but A and C, you can see if we use our cursor and move it across, we shall see that they overlap. They overlap within each other. So there's no difference between A and C. And then C and D are also different, but also B and C is different. Even B and D are different. So the same words you've used on the table is what you use here. Now you can choose to present the table or the graph, whatever you feel you want. Okay, but don't present both because it's the same information you're going to explain. So to avoid your supervisor saying repetition in your book, the red marks, you know, these red marks also appear in your project books, and you're like, oh my goodness, the project is full of reds. Oh, you even get scared of reading those reds. No, never get scared of those things. you know. Okay, let's go ahead. I'm going to stop sharing. Okay, let's share the screen again, the R screen. So what I'm saying that when you start doing a master's or PhD, you have decided that you're going to show the world that you good. Don't go in the middle of the journey and you chicken out. Now I'm going to give this example. I hope it doesn't offend anybody. It's like if you expect a baby after 9 months, and then when it comes to 5 months, you tell the doctor, you know, I no longer need this baby, you know, I am scared of giving birth, yet you want babies. So it doesn't make sense, you know. So it's also like a PhD or a master's. So in the middle of the PhD, when things get tough, that you even get too many reds even in your book, don't give up, just continue, because others can, you can, you know. Okay, so let's go back to the R script. I'm going to enlarge it. R script respond. Okay, so we run our command bar.group, and I have here other commands also for running the error bars. It's the same thing, so you can do that back home. We want to check for constant variance. You remember that under analysis of variance, we assume that the residues are normally distributed with constant variance and mean 0. So we want to find out, are those assumptions violated or not? Remember, have I performed a target test? Somebody is saying that why perform a target test? I don't know whether you're asking whether you should perform a target test or when. No, actually there are many multiple pairwise comparison tests you can choose from. LSD is one of them. There is Bonfera and there is Turkey. You can actually use the Turkey test and go through the same procedure. Below the notes there, I think there's also a Turkey test there. So you will have, not today, but you can practice. It's included in the script. You can also use a Turkey test. All of those multiple pairwise comparisons will give you the same conclusions. But in most cases, we encourage you to use contrast, which we are not going to look at today. If we want to teach contrast, we need you to know some theories that we can't really teach in the remaining few minutes. So we will do contrast next time, but let's go to the basics. You can always perform a LSD, Turkey test, or etc. You will ask me, why contrast? Now, this theory I can give you. Contrasts are pre-planned comparisons. They are questions that you write when you're writing your proposal. For example, you would like to compare the exotic species and the indigenous species. You would like to compare within the exotics, you want also to compare them. And within the indigenous, you also want to compare them. So those are pre-planned research questions, and they are independent. The information in the exotic is not affected by the information in independent or indigenous species. So the contrasts are actually independent of each other. But the treatment pairwise comparisons are not independent of each other. And there is a problem which occurs when you use treatment pairwise comparisons. The significance level changes from 0.05 to another value. There is a formula actually you can prove that the more the comparisons, the greater the significance level. So it keeps on increasing. So there's that problem, which was sorted by using contrast. But for you to understand contrast, we need to go and do the theory, also write out the contrast, and then we do the R. So for today, you'll excuse me, we will only do LSD, and the Turkey formula is also given. Okay, so I was saying that bar.error gives you the same result we've just seen. Then I want us to look at the assumptions under Anova. So we can use plot in bracket the model. So when we run that, if you go below here under the consoler, they say hit return to see the next plot. So I'm going to put my cursor under the consoler and hit return. So if you hit return, you see we are seeing a residual plot, which is testing for constant variance. So remember that these are groups of values. We have species A, B, C. That's why you see these groups here. We have the first group here, the second group here, the third group here, and the fourth group here. But all the same, the values are just a random scatter of points. You cannot draw any pattern in these values, just a random scatter of points. And once you see a random scatter of points in this graph of residuals versus fitted values, then it shows that the variance is constant. Hence, you've not violated that assumption. So it says hit return to see the next. This one is testing for normality of the residues. You can see that our points are lying on the dotted line, indicating that our data is normally distributed. So we've not violated the assumption of normality. It says hit to see the next. So this R is just being so generous. It keeps giving you. So there's this standardized residuals versus fitted values. So in the first graph, it used residues, but here it has standardized them. And we can see that the graphs are similar, only that the labels are different now, giving you the same information, showing that there's still constant variance. Hit return to see next, and now it gives you an empty one. Now, the reason why it has given me an empty space, it's because of the size of the windows. So if you do Ctrl minus, I have already minused. So if I hit return again, I don't need to do that, but if you adjust the sizes, you will see the plot. Okay, so we can actually produce those 4 plots just like my colleague did. I'm just going to go through only one. The rest you people will practice. Let's combine all the 4 plots in one panel. So we use the Power MFR. We are looking at the rows. It is placing the graphs in rows. So let's run that. And we run the next. So it produces these. Let me zoom them out. Stop sharing. And then share the Zoom plots, share. Okay, so we have our residual plots, which we've talked about. This is testing for constant variance, and because it's a random scatter of points, it shows that the variance is constant. This is showing normal distribution of the residuals, and the points are lying on the dotted line, indicating there is normality. Now, I also talked about these groups. It also confirms that actually analysis of variance should be the right method of analyzing this data, because you can see these are groups. We can't attach a regression here, you would be very wrong. And then we have standardized residuals versus fitted values. It is this same plot, but now we are using standardized residuals instead of residues. Okay? Okay, so let's leave this test and we go to the next part. Before I go to the next part, I'll remain in R and ask you in the chat, is there any query? Where is IA? What do you mean by IA? Okay. Okay. So the next part, You see, somebody was saying, can we use Turkey? So the next section, I'm going to leave it for you to practice so that we can look at the randomized block design. So this part here will give you the same information. It is a Turkey test of the same results, and the results are going to be the same. I just brought it in for those who want to do a Turkey test instead of LSD. So this you can run at home, and if you get stuck, I repeat, if you get stuck, I know you know my email. You can always email me. I'll answer your query, but I don't want to get 1,000 emails that go. I may not be able to respond to them. So if you get stuck, please, you are welcome to email me. But the other thing is, for you to do Turkey test, you need this package called MultCompView. So you need to install it. We are not going to go through that. On your computer, then load it. So we are going to leave that for you people, and you run it. Since you have the data, you practice, it gives you the same output, you'll be able to interpret it, okay? And if you get stuck, before you email me, go to Miss Google. I'll call Google Miss because I'm a female. Miss Google, okay? Or Mrs. Google, or whatever, Dr. Google. Pardon? That they are your children forever. Okay. So now we are going to look at two-way Anova. And the data we are going to look at comes from a randomized complete block design. I want to go back to the PowerPoint, but I'll just come here and let's go through the R script. The PowerPoint is very clear, but the R script you may get stuck, and email me when I'm not available, but you want it so much that you need help. But always go to Google if you need help, and I will also help you. As you said that you are my children forever, that is true. When you're a teacher, you get children, you give birth to adults, and you get so many, and I am happy to be one of those who gives birth to adults. Okay, in a randomized complete block design, I'll give you a bit of theory. We use this type of design if we know that there is existing variability in our experimental site. For example, we know that there is a slope gradient, or we've gone to the field where we are going to perform our experiment, and we've found out that actually the color of vegetation changes as you move through the site. Some bits are yellowish green, others are dark green, others are green. You know, there is variation in the color of grass. In that case, what you do is you're going to divide your area, your site where you're going to perform your experiment, in those different colors. Colors are now going to be your blocking factor, the color of vegetation. Now, what if there's no vegetation? You take a random sample of the soil. So you sample different corners, label them, remember to label them depending on the point where you obtain them. If you do not know how to label, use a GPS. Go with your GPS and get the GPS points, so that when you come back, you know that is the point where you've gotten sample one. Because I know experiments, they can confuse you and keep repeating yourself, use a lot of resources. But if you plan well, everything will move out smoothly. And I'm telling you, experiments are the easiest to analyze because you already know what you're going to do anyway. It's not like a survey where you say, maybe I can also use a logistic. No, now in multinomial, you see what I'm saying? If it's a randomized complete block design, it cannot change to be a factorial, or it cannot be a Latin square design, you see? So you know what to do with an experiment, and you're good to go. So block according to a known source of variation, and place your blocks perpendicular to the direction of variation. That is when you will maximize the variation. After citing your blocks properly, then divide the blocks into plots where you will randomize your treatments and then apply them. Okay? So we assume that you now know that bit. So when it's called randomized complete block design, it means that we have equal replicates. Treatment A is equally replicated. We have 4 replicates for all the treatments. Now, if you do not have enough resources and then you replicate A 3 times and B 4, C is replicated 5 times or 2 times, that becomes incomplete randomized block design. And the analysis changes. Don't use the same analysis. You have to account for that difference in replication. So you go to Mr. Google and say, how do I analyze data from an incomplete block design using R? And my dear, you will get information, you'll not be able to read it. A lot of information has been placed online. You people are very lucky. In this era of technology, there is a lot of information. When I was studying, you would get 4 or 5 manuscripts to read, and then you have you have to struggle to get so many information. But this is an era of technology, and there is a lot online. Just read. You must make sure you read. You have to cultivate the character of reading. Remember that if you're doing PhD, even before you defend, you have to check whether there is new information which has come up in your area. If you forget to read it, that will be the first question that comes in your defense. That is I'm just stealing questions for you so that you know when you get that question, you always remember me. Okay, thank you. Now let's go to analysis of variance, two-way analysis of variance. Now the data we are going to use is called yield. We are going to import yield from Excel. It has a CSV extension, and Dr. Helen has already shared it. I hope you've picked it. Now, if you do not have this script, please write yield. You can use an equal sign, read.csv in bracket, quotes, yield.csv is the data you're importing. You are still calling it yield. It is very interesting in R, you use the same name and it doesn't complain. Because if you go to SAS, you may not use those same names to import the data. You might have to change, you call it yield 1, so that it knows this is something it is doing. Okay, so now let's run that command, which we've run several times, and then we print it. And below here, we are going to see if I move my console. Oh, there are very many values. Oh my goodness, I cannot. Let me see. If you go to the environment, you'll see yield. And if you click on yield, it's going to appear where your script is. So yield here has block, it has variety, and it has yield. Okay, so here we are looking at yield of, it should be grass, different types of grass, and we are looking at yield after certain cutting dates. Or it should be maize. I've forgotten the background information about the experiment. Okay, so I am going to close this one. You see on the top of the menu under Studio, you can X out yield and go back to your script. So for us to run analysis of variance, you use, I'm calling this model fit. I assign an AOV. You can use linear model. Yield is a function of block plus variety, comma, and the data is equal to yield. So let's run that and see what happens. So we run and we say summarize that model. So when we say summarize the model, And I'm going to increase its, so we can see here we have our output. It gives us the block effect, the variety effect, residues, etc. But remember, we are only now interested in variety. We do not want to know about the blocks. The reason why we put blocks is to account for the variability that we cannot actually explain with our data. So the job of block is done. We are interested in the varieties, and the hypothesis here is that there's no variety effect, or the average variety or the average yield for the different varieties is similar. Alternative is at least one variety is different. And now when we look at the p-value corresponding to the variety, we see it is 2.55 times 10 to the power minus 5, which is 0.000. Now you can see these stars here, and look down here. It is saying significance codes, that this value variety is significant at 0.1%, at 1%, and at 5%. So that is what these stars mean. It is significant at 0.1%, 1%, and 5%. So we have evidence to reject the null and conclude that at least one of the variety is different. Now we want to find out which variety gives what mean. So we are going to go back to our script. And what I've done is to do an LSD the same way I did it for analysis of variance. I'm bringing it here. I'm calling the object ls1 because I've already used ls is equal to lsd.test. Fit is the model and variety is what I want us to run. So when I run that, invalid something, let me see my warning. Let me try reducing. Pardon? Okay, so let me run it again and see whether it works. It might be because of my Let's see whether it will give me output. It is complaining, but still giving me an output. Yeah. The problem is the size of the window. It said invalid graphic state. Yeah, it is the size of the window. Let me remove these graphics so that they stop giving me these red marks. We might get a heart attack because of these graphics, the red marks. Graphics off. Then I run that. So it goes, then I do not have to have problems with the red marks, but it has run the output. So I'm going to increase the size of the font. Okay, so let's look at the output. I'll look at the comparison. You remember somebody asked me about what if the mean has AB on the same letter? How do we talk about that? So this is what we are looking at. I have highlighted it. And we saw that in our analysis of variance table, the overall Anova test was significant. That's why now we are testing the means to find out which mean is statistically significant from the other. We say that this is LSD, and in R, it attaches letters for you. In other packages, you don't get these letters, by the way. I'm not drumming for R. I don't even know who made R. So I'm just telling you the advantages between the packages. And how do we interpret these A's that are highlighted here? We say that means with the same letters, with similar letters, are not statistically significant at 5%. So we start with E and D. They have similar letters, meaning they are not different. Even when you look at the magnitude, we see that E is 12.76 and D is 12.59. Seriously, we shouldn't find significant differences. So they've been attached similar letters. Let's go to F. Now, the magnitude of F is 10.82. That is the yield for F. And you can see that under F, they've put AB. Okay? They've put A because F is not statistically different from E and D, but F is different from A and B and C. That's why you see a B coming here. Let me repeat myself. E and D are not different because they have similar letters. When we come to F, mean F, let me highlight, mean F, the letters are A, B. So we first interpret A. A means that F is not different from D and E, but F is different from B and C. The treatment B and C. But at the same time, F is not different from A. Have you seen that? Because this B is appearing here, below here. Are you picking? Are you understanding? Let me see the chart. Whether... Yes, okay, great. That is excellent. Some people are saying not yet. Okay. So we are still interpreting. So we said E and D are not different. F is not different from D and E. And F is not different from A. But it is different from B and C. Then we go to A. A has letters B, C. A is not different from F, but it is different from B. No, actually, it's not different from B and C because we have a C attached. Are we understanding? And then B and C are not different. So somebody asked that question and the answer is right here. You can have actually two letters so long as you know how to interpret them. Then we can produce box plots also for that data, just like we did before. We can produce, and you can see that because we've made our graphic window very small, you see that what was in the LSD interpretation is what we are seeing here. It has put the AAs, AB, BC. Okay. So the last thing I wanted to run for you, because time is out, is to run a bar chart. Oh, sorry about that. I must have not changed anything. Okay. So you can see that, ladies and gentlemen, you can see that I'm producing the output for the previous model, the CRD, because I've not changed the object LS. I was still keeping LS. So I put in a 1, which is our model now here under RCBD. And let me run it again and see. So there we are. So I'm going to make my window larger or zoom it out. Oh, it has still the same effect. Let me. let me, I can what? Yeah, I'm going to do that. Okay, let me share the box plot. The error bars are here. One thing is I didn't change the limits, so that is the reason why I have a crooked. Let me just zoom out, correct something in my script. If we go to the script, okay, here I am ranging between 0 and 15. Let me range between maybe, because the means you can see they start from 8.8, so I range from 8 to 13 probably, and see maybe 14, and see whether it improves. So I draw another bar chart. Okay, then I go down here, I change. We give it 15. Okay, this is better. So what I've done, if I've changed the limits for my error bar graph, instead of having 0 and 40, I put in 7 and 40, and that corresponds to the values of the means we are producing in the consoler. That's where I pick them from. So let me zoom it out so that we can see that and share it with you guys. Okay, share. And this is, I think, the last thing we are looking at today. So you can see that we can construct again our error bars. We see that A and B are not different, and they are not different from C. They are overlapping. I think you can see that very clearly. But C and D are different. They are not overlapping. The same applies to B and D, but B and D and E are different. Even E and F, they look different also. Okay. So because of time, I want to stop here. Let me go back to the R script and talk about it briefly before I stop, so that you're comfortable with it. Okay, the R script, what I'm left with to talk about is this we've already done, constant variance, testing constant variance, multiple comparison we've done. The only thing I didn't talk about was factorial design, which I want you to go through. It is very clear, there's no mistake. The only thing I'm going to comment about factorial is that once you run it, the first thing you interpret is the interaction. Don't look at the main effects before you interpret the interactions. And if the interaction is significant, meaning the p-value corresponding to the interaction is less than 0.05, then you draw interaction plots. I don't know whether I can be given 5 minutes. Can I be given 5 minutes? Yes, I've been given 5 minutes. So if you allow me and pay attention, I want to quickly run the factorial. So I expect fewer questions, because the more the questions, the more time we need. So just pay attention. We read the data called factorial.cvs. So I'm going to read that data very fast. And I'll run it. And then I want to see what is in factorial. In the factorial, I have nitrogen, I have the type of crop, and I have yield. Then you can run structure to see. In the structure, I have the data frame with 48 observations, 3 variables, There's nitrogen, which is being called an interval. Crop is a character, yield is numeric. So we are going to change nitrogen and crop to a factor for us to be able to do the analysis. And I know you know that, but it is right here. I'm calling it fact. Pick nitrogen and change it to, no, the object is fact $nitrogen, change it to a factor, and you're going to pick that from fact $nitrogen. So let me run that and confirm, yes, it has been changed to a factor. Then also run for crop, confirm, it has been changed to a factor. I'm running the model. The only difference here, ladies and gentlemen, I'll call you my colleagues. We have model 3 is the object. We use the A of V, and yield is the response. It's the function of nitrogen multiplied by crop, because we want to get the interaction. Okay, and data is called fact. So let's run that and run the summary. So we pay attention to the results quickly. So when we look at the results, we go straight to the interaction. And once it is significant, then we go and draw interaction plots. We are not concerned with the main effects. These are the main effects: the effect of crop, the effect of nitrogen. Yeah, the nitrogen effect, the crop effect. We are now concerned with the interaction once it is significant. If it's not significant, then we are going to look at the main effect of nitrogen and the main effect of crop. I encourage you to read about factorial more. Then we find that there is an interaction between nitrogen and crop. What does it mean? It means that the yield of the crops depend on the different levels of nitrogen and also the type of crop. So yield, for you to have an improvement in yield, you must have a different level of nitrogen and also a different type of crop. When you move that and change, we will get different yield. That is interaction. Let's go very fast and draw the interaction plots, which I've given you here. I'll first run graphics off and then run our interaction. I'm sorry I didn't interpret how to, but I believe I want us to know about this plot here. I'm going to share the plot. So my plot is so plain, but you can make it more beautiful with different colors. And let me also do this so that you can see. It is not giving me the types of crops, but below here you can see the different types of crops. This is the interaction plot. If there was no interaction, we should see parallel lines. But our lines are not parallel, meaning there is interaction, meaning that at zero level of nitrogen, when you move from, this one is called guinuts, and move to another crop, which is called alfalfa, there are differences in yield. And when you move to soya, there are differences in yield. But this particular plot is showing you that you actually don't need fertilizer for soybean. You don't need to add nitrogen for soybean. I think this is, from biological point of view, soybean is a nitrogen fixing plant. If I'm wrong, you can correct me, but that's what I know from biology, that soybean is nitrogen fixing plant. And if the soil is fertile, you don't actually need to apply your nitrogen, because you can see at zero nitrogen, we have the highest yield. As you apply nitrogen, the yield is decreasing. Okay? So from here, we can actually recommend to farmers that if your type of soil has a similar characteristics with where this experiment was performed, then you can actually do away with adding nitrogen. You will get a higher yield compared to when you apply nitrogen. And when you come to this dotted, small dotted is groundnuts, this one here, where I'm moving down, You can see also groundnuts is a nitrogen fixing plant. And you can see that when you apply any more nitrogen, the yield is decreasing, but at 0, the yield is higher compared to other levels of nitrogen. And when you look at this one, which is called alfalfa, the same story. The yield is higher at no nitrogen. But when we come to guar, for it doesn't matter whether you're adding nitrogen or not, the yield you can see is constant. So this is a pictorial diagram for an interaction plot. We can make it more beautiful by varying these colors, you know, putting in the aesthetics so that the graph becomes more beautiful. Okay, let me go to the chart. Do we have any question? How can we deal with missing values? Is it a whole replicate missing? For experiments, if it is a whole replicate missing, then the type of analysis changes from randomized complete block design to incomplete randomized block design. Please explain where the lines intersect. We've talked about interaction, and we said that if there was no interaction, we would have parallel lines. But if we have interactions, that's why you have lines intersecting, meaning at 50 nitrogen level, we can see that all of these treatments are decreasing in yield, and still soya has the highest yield at 50. That's why you see those crisscross lines. Okay. Interaction. This is the last thing I'm explaining. I would like to give a chance to forum staff. I'm only explaining about the interaction. Then we stop here. So I'm saying that interaction. We saw that there was a significant interaction between nitrogen and crop, meaning that the yield of those particular crops depends on the level of nitrogen you are at, and also the type of crop. And this has been displayed in our graph. You saw that at 0, the different types of crops actually have different yield. And when we move to 50, also the different types of crops have a different yield. So that is the interaction. Now, that is the last thing I'm explaining. Unless if you have a burning question, I am requesting you that you fill our monkey survey quickly and post it back. We need your feedback to improve our training, but we thank you so much. Our markdown will be talked about the next training we hold if God allows us to hold the training. Okay, so thank you so much. Participants, you've been so patient with us. You've been so consistent. We are so, I have no words. I've even, the words have disappeared. Thank you. Please fill in our monkey survey. And I want to hand over to Dr. Ranyararo to say something. Thank you very much.
I know my name is hard, but it's Ranyararo. Thank you so much, Professor Susan and Helen, for facilitating this training. We are so grateful. We are so happy that the attendance was so great. I'm sure the participants are also very happy with the delivery of the training. Like what Professor has said, that there will be follow-up training. We shall be updating you on the follow-up training, when it will be, and also we shall share what will be shared in the follow-up training as well. I would like to thank every one of you for sparing time to listen to how you can manipulate R in the data analysis. I'm sure this has been helpful to all of you. I want to say that we have this training on YouTube. The professor and Dr. Helen have been sharing the links for this training, but still you can get in touch with us if you would like to get the YouTube links and also the data which was being used in this training. We also have the links for that. So please get in touch with us if you need any. You can get us on our email and we will be happy to share with you. Thank you so much, all of you. I would like to give an opportunity to my colleague, David, who was our IT specialist. We've been helping us to manipulate the system to be able for us to be able to deliver this training to all of you. David, I give you an opportunity before we officially close. Amitu, the floor is yours.
Thank you very much, Jolene. I would like to thank all the participants who have persevered with us for all this time, and we shall make sure that you have all the documents and plus the recordings through the YouTube links. And we have been sending, Helen has been sending you, and Susan has been sending you the recordings. So we shall, even this one we shall send, and we shall make sure that all of you are up to date with the content. We have also opened a drive link for all the materials, and so we would like to thank all of you for following the training up to the end. And as Jolene said earlier on, that there will be a follow-up training. So we shall make sure that we learn from what didn't work on this one, such that we can improve. But we shall always try our best. So thank you very much to you, all participants, and also our facilitators.
Thank you, David. I also want to tell the participants that, yes, we are going to provide the certificates of participation. We shall be sending to all of you who have attended, and we shall be sending to you via email, because I know all of you have registered, and we also have your information on attendance. So we shall be sending to you. If you have any question or query, we encourage you to just get in touch with us via email. We'll be happy to help you. But before I close, I want to give a chance to also Helen to say something before we close.
Okay, thank you so much, Dr. Nyararo. It has been a great experience. I mean, doing the training on Zoom with a very big number of participants. It's been a great interaction. As I give my concluding remarks, I kindly ask you that you fill our Survey Monkey form that I've sent out. We kindly encourage everyone to fill in, because we need that feedback such that we're able to know where to improve in the follow-up training. I encourage you, R is a very interesting program. Kindly make sure that you always use an updated program. In case it is in case it's not updated, go ahead on internet and update it. If all the necessary commands have been installed, all you need to do is to load the libraries, just that. And it is a free software, you're not going to buy it, but it's just, and when it comes to a programming language, it's about practice, practice, practice. And in the process, you'll be able to solve the different errors as you move on here and there. Some members have been talking about the R Markdown. It is also something very easy. It's the same as the R script. I encourage you, if you find time, just go in your R studio and then follow the same procedure as the R script. You see the R Markdown, and it's something very interesting that can enable you to transfer your commands into the Word document, because most of you are saying, what about the R Markdown? How to transfer the work into the R documents? But it has been a great experience. Thank you so much, and wish you the best in your endeavors. Back to you, Dr. Nyararo.
Thank you, Dr. Helen. Thank you, everyone. I'm seeing the comments in the chat. Thank you so much for this time. At this moment, I would like to say bye.